theorist at our own department. So we hand it over to her now. She will be in charge now. Over to you, Prabha.
Thanks, Ayan, and welcome everyone to the concluding session of this wonderful Dual Mysteries Conference. First speaker for this session will be Brian Swingle from Harvard University. And without further ado, let me just ask Brian to give his talk. Over to you, Brian.
Great. Thanks very much to the organizers for inviting me, for you all coming out at these strange hours to listen. Yeah, and I propose to talk to you about some subjects in quantum electrodynamics, specifically about chaos. And I'm very happy if you have questions, you can interrupt me during the talk. It's great. I welcome that kind of interaction. So yeah, so let's jump in. Let me just tell you what I'm going to do. So I was sort of thinking about the theme of this conference and trying to decide what I should talk about. And I sort of thought it's the last day, at least of the main scientific content. And so maybe it would be fun to talk a little bit about electrodynamics, which I call the original gauge theory, which I think is true. And it's not, of course, directly a holographic theory in the conventional sense. At least it doesn't have Einstein gravity dual or anything like that. But chaos is broadly related to these dual mysteries that we're all thinking about. And chaos in quantum electrodynamics is actually quite an interesting subject. And in particular, I hope to convince you that there's still some surprises in store in QED, especially in the presence of interesting sources. And for me personally, what excites me the most is that it's a subject we can study in experiments, and that there are actually unexplained observations that we'd like to understand better, and that quantum chaos, thinking about quantum chaos, will help us understand. So because the audience is potentially broad, I want to start by reviewing quantum chaos as diagnosed by the quantum butterfly effect. So there are lots of ways to think about and try to diagnose quantum chaos. This is one of them. There are other ways. For example, you can look at the spectral properties of energy eigenvalues, how they're distributed, how they repel or not. That's another way of characterizing quantum chaos. They are all related in some ways, but I won't talk about that. So I'll just talk about this quantum butterfly effect, and I'll remind you what that is. And then I'll discuss two examples. The first example is from the nuclear magnetic resonance community. So it's looking at the interactions of magnetic dipoles in some particular material, which I'll discuss later. And then the second is a more engineered situation where we're trying to put a control atomic ensemble inside an optical cavity. And the strong atom-like coupling will give us interesting new physics. And I'll talk about how we can use that to try to engineer fast scramblers in the lab. Okay. So that's the basic plan. Let me get started now. So let me start with quantum chaos. So to start quantum chaos, we should first remind ourselves about classical chaos. And to me, I think, again, this is a very rich subject, so there's many ways you can think about it, but I like to think about it in terms of a dichotomy between sensitivity and thermalization. So what I'm going to show you here is a stadium, a billiard, and this little blue array is a bunch of point particles that are going to move around in this billiard. And they're all started nearly the same place, but with slightly different initial conditions. Okay. And if I let the system go, you see they sort of move together as a package at first, but then they kind of spread out. They start to each follow their own very different trajectories. You can still see some kind of back and forth motion, but after a while, it's more or less like a totally random looking collection of particles. So the dichotomy here is that each individual particle follows a detailed trajectory that's sensitive to the precise initial condition, but the overall outcome when you have this collection of particles is that the system looks kind of uniform and simple. It looks thermal. It looks like it's in equilibrium. And this is one way of thinking about sort of classical chaos. And a natural question we can then ask is, how does this translate to the quantum world? And this is also a very old subject. From this point of view that I'm advocating here, it's useful to think about sort of what's the smallest possible perturbation you can make to a system. We're used to thinking of, in the in the jargon of butterfly effect, the flap of the butterfly's wing is supposed to be a very small change, but it is still a distinguishable change. It's a change in the state that's sort of orthogonal in the quantum language. So the smallest possible perturbation that we could consider would be just flipping, say, one quantum bit to an orthogonal state. And as I'll at least touch on briefly later, this kind of questions of quantum chaos are very important in quantum gravity and other contexts, but they're also being brought to the fore now because there's new experimental possibilities already here and on the horizon, where we're actually able to manipulate and study the dynamics of these isolated quantum many-body systems over long enough times that we can see the effects of chaos, we can see the effects of thermalization, and we can study this physics. So on the right, I just show you one example of this, courtesy of the Bollinger Group in Colorado. This is an array of beryllium ions in an ion trap, and they can address these ions, control their motion in various ways, and cause the spins attached to these ions to interact in some interesting way, so that we could actually hope to probe physics of the sort that I'm telling you about here. Now, let me give you a concrete theory example, something to hold on to when you think about the subject. So let's think about it just a spin chain. And to illustrate the quantum version of what I'm calling the quantum butterfly effect, let's think about the evolution of two states. So the first state will be the state psi1, which has all the spins in the up plus y direction. And the second state, psi2, will be the same thing, except that the first spin is in the down y direction. So these are two orthogonal states. You can check that they have the same average energy when you compute the average energy of this Hamiltonian. They both have zero average energy. They're at the center of the spectrum. This is a discrete spin system, so it has a bounded spectrum. The center is where you have the most entropy, the center of the spectrum, that's zero energy. And I've chosen these J, HX, and HZ, these couplings, so that this Hamiltonian is chaotic in the sense that I want. What that means is, although the states psi1 and psi2 are perfectly distinguishable at initial time, you just measure the local spin on the first site. As time progresses, as I evolve with this Hamiltonian, they will remain, of course, perfectly orthogonal as quantum states, but it becomes harder and harder to tell them apart with simple measurements. So here's an example of that. On the x-axis, I'm plotting time, evolution time in units of 1/j. That's the nearest neighbor interaction strength. And on the y-axis, I plot the expectation value of the first spin. And the blue line is what you get for state 1, and the red line is for state 2. And so you see at early times, you can clearly distinguish these two states, but then at later times, they actually have a very similar trace as far as this expectation value is concerned. And in fact, if I covered up the early part of the picture, you might have a hard time telling me which one came from the spin up and which one came from the spin down state. Of course, I've shown you just one example here, but this is actually indicative. If you look at any other single expectation value or pair of expectation value of 2-body or 3-body spin, you'll find that they're all similarly small and close to zero and close to each other in this system. They're close to zero because since I'm at the center of the spectrum, the thermal equilibrium state is the maximally mixed state. And so the expectation value for any observable should just be zero in equilibrium. And that's why it's converging to this equilibrium value. So these are two states moving in Hilbert space, very complicated, totally different, orthogonal, but nevertheless, they look the same for all kind of local probes. And that's, again, they're following very different trajectories. That's a sensitivity in some sense, but they nevertheless look for many practical purposes like they're in equilibrium, like they're uniform and simple. That's thermalization. So a fun analogy, if you've ever had the pleasure of assembling an IKEA chair or furniture of any type, you know that it can be pretty frustrating. All these pictures with no words. Here's a particularly bad one on the left here, the paradox play table. So an analogy is like, imagine you are making a cabinet or something, and you get to the 34th and final step of your cabinet, and you notice that there's a screw missing, and you missed a screw in step 2. Well, more or less the only way to fix this thing is to unbuild the whole cabinet back to step 2, put the screw in, and then rebuild it. So the cabinet in detail is very different with or without the screw. And it's hard to put the screw back in without kind of reversing time, if you will, without rewinding the system. On the other hand, this thing looks more or less cabinet-like, regardless of the screw or not the screw. And so you might think, okay, it doesn't really matter. It's still a cabinet, and that's thermalization. Now, there's a very precise version
Brian,
of this. Yeah.
Brian, can I interrupt you about the previous slide, about this
Please.
slide before this?
Sure.
So you have this red and blue curves. It looks like they're converging while they're already oscillating, but when they're thermalized, they shouldn't oscillate, right? Is it just a coincidence for these two special states?
Are you referring to this initial oscillation or to the like oscillation at later time?
The late oscillations, right? Because after the thermalize, they shouldn't oscillate.
Yeah, so this is a small system. It's only, I think, in this case, 14 spins. So there's definitely going to be some finite size fluctuations. Now, it's true, I would say this looks like a more regular oscillation than you might expect. So there's probably some, I'm not sure, I'm honestly not sure what exactly explains that seeming regularity. So that's a good question. The fact that there are some wiggles at late time is not unexpected, but the fact that it seems to have a definite period, or seems relatively close to having a definite period, is less clear why that would occur. I don't think there's anything sort of physically novel going on here. There are systems like quantum scar systems where you can have these kind of oscillations at late time. I don't think that's what's happening here, but I don't have a super clear, like a super simple explanation for why it looks sort of relatively periodic.
Thanks.
Yep. Okay, so, right. So we have these two states, psi 1 and psi 2, and we can ask how they're related to each other. And the way they're related is very simple. You just rewind time on psi 1, you apply the spin flip sigma 1z, which flips the spin from up to down, and then you fast forward time again, and that would take you to state psi 2. So in other words, psi 1 and psi 2 differ by a Heisenberg operator, this thing you learn about in quantum mechanics. And I think this is actually it's a nice kind of way to think, because it's very similar to the classical butterfly effect, where you have two initial conditions that are close to each other and then diverge as you go away. Here, we're just doing a slightly different version of that thought experiment, where we're starting at some point, say here, the end of the orange arrow, we're going forward. And then if we went backwards in time, we'd end up at exactly the same place again. But because we make this small perturbation, then when we go backwards in time, we end up at a very different place at the end of the day. Okay, so let me give you just a cartoon of this. So this is going to be a space-time diagram. I got a space on the x-axis and time on the y-axis. Each of these black lines is like the world line of a qubit. And you can think of the evolution as like a bunch of boxes. So think of this as like the trotterization of some Hamiltonian evolution. We can always approximate any evolution in this way by these stacks of boxes, which are just like two qubit interactions. But for our purposes, let's not worry about the details. Just think of it as some kind of interaction, right? So the orange boxes are forward in time. The purple boxes are backwards in time. And the rule of unitarity is that if I don't do anything in between, then these boxes just cancel and I get nothing at the end of the day. Okay. Now let's ask what happens if I throw in this little fly in the ointment, the butterfly's wing flap. I flip this one spin. So now I try to do the cancellation, and most of the boxes cancel, but some of them don't. And in particular, the ones that touch this butterfly don't perfectly cancel. And more than that, the actual non-cancellation or the obstruction has spread now from one site to two sites. So I should color these things blue. I'm not saying that it's sort of like a simple operator on this configuration. It's something complicated, but in principle, it has support on both sites. And it's therefore spread from a single site to two sites. And now we can do the same thing again. We cancel, and the perturbation is spread some more. We can keep canceling, it keeps spreading, and it keeps spreading like this. So this is a very simple cartoon of how this single spin flip would spread across the entire system in terms of its effect on the dynamics. You can see also here from this diagram immediately that there's some kind of like light cone-like structure emerging, that this effect is going to spread in a way with these local interactions that's linearly growing with time. And we'll come back to that later. Now, it's also interesting to consider what happens if I have a system where the interactions are all-to-all, where everyone can talk to everyone. A simple model of that is to have a system where you randomly select pairs, and those pairs can then interact like this. That could be one set of pairs that interact, or like this. So now I'm showing you snapshots at moments of time. And so now we can again put our butterfly in there. We can say lay down random interactions. And you see the rule is everywhere that the butterfly, every blue thing, every place the butterfly is touched, as long as it overlaps with an orange bar, it means that the perturbation spread to that new site. So the perturbation spread up there. Now you see that with high probability, the interactions are going to take these two perturbed sites and spread them to two new sites. And then with high probability again, those will also spread. So that the affected region doubles roughly every time step, at least until the number of affected qubits is of order the total system size. So this is a simple cartoon to see how you can get exponential growth in the number of affected spins in these all-to-all systems. And that's something that we're relatively familiar with in the context of quantum gravity, where this is described in the dual picture in terms of shock waves and the exponential blue shift as you approach the horizon. Okay, so how do we probe this cartoony effect? Of course, this is a cartoon. Things don't just definitely expand or not expand. There are amplitudes for everything to occur, just like as usual in quantum. So we have this operator W of t, and we have sort of amplitudes for all possible ways it could grow. It could grow relatively fast, relatively slowly. There's some sort of intermediate behavior which is dominant. And we can probe this, what I call quantum shape of this operator, by trying to detect how far the operator has spread using some other probe. Here's a cartoon which explains how that works. So suppose we have this spatial case again, and we've spread our local operator, over say now 8 sites. The red thing, the V here, is the probe. And you can see that if we apply the probe to a region where the blue perturbation is not spread to yet, then it doesn't matter in what order I apply the perturbation in the probe. I can apply the perturbation first, then the probe, or the probe first and then the perturbation. And by contrast, if I apply the probe in a region where the operator has spread, then these things don't commute. And the degree to which this commutator, the non-commutativity of these two operations, that degree of non-commutativity can be a measure of the relative size of this operator. That leads to the notion of a commutator. The commutator defined here. The simplest thing you could think of would be to probe the expectation value of this commutator. That's a nice object. In particular, it's easy to measure in experiments. It's just linear response, well, relatively easy, I should say. Nothing's completely easy, but relatively easy to measure. It has a clear physical meaning. But precisely because it has this clear physical meaning and because we're studying a chaotic system, it's actually not so useful for our purposes. The reason why is that because it measures the response of the system to a perturbation, and because we saw previously that perturbations, in terms of their simple response, die away, that means this object, this retarded correlation function, this commutator, is going to just vanish at late time. So it's not going to provide a useful measure of how big the commutator is. The commutator as an operator can still be highly non-trivial, but its expectation value happens to be 0. So then the next simplest thing would be to look for the, say, second moment of this operator. That's called the squared commutator, and I show that here. And this is kind of the central object in a lot of studies of quantum chaos these days. Anything focused on this butterfly effect physics or out-of-time order correlators, that's all kind of encapsulated in here. And so by choosing W and V to be different interesting operators, and by looking at different kinds of interesting time evolutions, we can use this object C of t to diagnose various aspects of chaos, operator growth, perturbation spreading, etc., in interesting systems. So you can all make your discussion in terms of out-of-time order correlators, which I will define in a little bit. But I think this commutator point of view is kind of the key physical way of thinking about things. Okay, and that's the point of view that I prefer. So then if you go back to our local system and you ask, okay, in this local system, how does this commutator look? Well, it's just a nice, physically sensible version of the cartoon we showed before. If you fix the time and look at the commutator as a function of separation between the perturbation W and the probe V, then you would expect when the probe is close, the commutator is strongly non-zero. When the probe is far away, it's zero. And there's some kind of interesting crossover where it goes from being strongly non-zero when V is close to W to being close to zero when V is far away. And that's shown by this profile. The fact that it approaches a uniform constant in the center is something that we can understand easily enough, but I'm not going to dwell on here. If I instead look at the space-time contours, the contours of constant commutator, then there can be interesting structure near the butterfly, near the wing flap, near the operator W. But further away, you would typically find in a local system that the contours approach asymptotically straight lines, and the slope of that straight line is defining a speed, which is called the butterfly speed. And it's essentially the speed at which this scrambled region in the center, this chaotic, fully non-commuting region spreads in space. Okay, and now before I finish this section, let me just also mention that a little bit of the history here. Actually, these kind of objects were first considered many, many years ago in the context of superconductivity. People were looking at nonlinear responsive superconductors, which led to like 4-point functions of momenta. And they discovered that what they consider, this is Larkin and Marchennikov in '68, they discovered that the sort of naive way of thinking about these things was not working, and they needed to include some extra physics to get the right 4-point function. And it turns out that the way to think about that in the modern language would be to say that these particles are moving in some chaotic potential and single particle potential, and that caused like a chaotic Lyapunov growth, which is encapsulated by this kind of commutator object here. Okay, so this is one of the reasons why, at the suggestion of Kataev and others, we initially started thinking about these exponents lambda, the exponential growth that you see in the out-of-time order correlator, as being analogous to chaos. And I'll give you other reasons for thinking about that in a second. And then, of course, the other thing which really got work on this started again in earnest was this observation that in ADS-CFT, you can compute these quantities, this object C, or some closely related version of it, and that they would have this exponential growth, which is characterized by a rate that's 2 pi times the temperature, and which is in fact the fastest that that growth can be in a quantum system in thermal equilibrium at temperature T. You could also see the butterfly effect, this velocity that I was talking about, and this suppression by the entropy here. If you ask how long it takes, say for x equals 0, for this quantity to become order 1, the time would be logarithmic in the entropy, because it needs this exponentially growing thing to overcome the 1/, entropy suppression. And that's precisely the log time scale that it would take for a perturbation to spread in an all-to-all system over many degrees of freedom, over order entropy degrees of freedom. So all these pictures fit together, and the cartoons I gave you are actually quite accurate. I would say 0th order cartoons of the physics. And then these commutators let us make it all nice and precise. Okay, so that's the introduction to, or really review of chaos. So I'll just pause here for a second. This is a good time. If you have any confusion about what I talked about so far, feel free to ask. Just pause for a few minutes.
Brian, I have a question about your trotterization, the trotterization diagram. So suppose we have MBL, how does that picture will change? I mean, what will be, because by the gates that you showed, it seemed that it will generically work, but what will go wrong?
Yeah, good question. So if I look at like this kind of picture here, essentially what happens is this is like an upper bound, where I'm just doing the cancellations that are guaranteed by unitarity and nothing else. And so maybe in a chaotic system, you think this is qualitatively not wrong. Like maybe the speed is different, and indeed it will be not equal to this speed, but it'll be slower. But it's still a qualitatively accurate picture. However, when you have NBL and you have localization, then you find that this picture is like qualitatively wrong, that things are spreading much more slowly. And essentially there's like more and more cancellation then there's additional cancellation that you wouldn't expect just from unitarity, but that follows because the Hamiltonian actually has many conserved quantities that keep things local. And these additional cancellations allow you to further truncate this light cone so that in fact it ends up being not a linear light cone, but a logarithmic light cone. It only expands logarithmically. And we can actually see that, we developed some tensor network machinery that lets you actually do calculations, and you can go to a localized limit and actually see that the information spreading just almost stops.
Thank you.
All right. Well, let me go on then. Feel free to stop me, but I'll move ahead. So in this talk, I'm going to tell you two new things, which you may not have heard before. In both cases, it's sort of a situation where QED is like the hardware that we're thinking about. It's the kind of underlying substrate. And when you have a quantum computer, you are using that substrate to do some highly engineered thing. So I want to consider some examples where we're closer to the substrate, where it really matters that we're doing QED, and tell you about how quantum chaos can manifest in the context of nuclear spins and in the context of optical cavities. So just thinking about thermal equilibrium is also interesting. There are a lot of questions there. A student of Subir Sachdev's did a calculation with me, Julia Steinberg, some years ago. We looked at QED3 at large and limit. You get some interesting answers. There's also interesting things to think about chaos when you have the full power of a quantum computer, but I'm going to focus on these kind of intermediate systems today. So first, let me talk about nuclear spins. And let me approach it by asking the question, how would you actually measure this commutator in an experiment if you wanted to? Well, this is where out-of-time order correlators show up. If you expand that commutator out, there's various kinds of terms. There's 4 kinds of terms. And the sort of hard kind of term, the term that's hard to measure experimentally, is what I call F. It's the out-of-time order correlator. And it has the form of an expectation value in some state of a sequence of operators that go from time 0 to time t, to time 0 to time t. Okay, that's why it's called out-of-time order. And you can think of it as an inner product of 2 states. And when you think of it in that way, what you're really trying to do is kind of exchange the order of V and W, which is back to this commutator idea that I was telling you about. I won't go through the details of this, but just to say that we made a proposal and people are trying to do that. But it turns out that this kind of experiment has actually been carried out in a different context for a long time, namely in the context of nuclear magnetic resonance. This goes back to the work of Hahn on spin echoes. This is a cover from Physics Today from the 50s, where Hahn is explaining the physics of spin echo. And the idea is you have like a bunch of spins which are living in the XY plane. So just think about a bunch of spin half degrees of freedom, and they're processing about a magnetic field in the Z-axis, which is out of the circle here. And each runner is a spin. And the fact that you find in these systems that each runner has a slightly different speed, which means they have a slightly different angular frequency because their local magnetic field environment is slightly different. And so when the referee says go, this runners all start to run, they run, and after a while, they kind of are all the way around the circle in various seemingly random locations. And the signal, which is the number of runners through a different given direction, is very small. That is, there's no net magnetization. But now the referee says reverse. The runners all turn around, they go back. They're all starting at different places, but their speed going backwards is exactly the same as their speed going forward. So they all perfectly recollimate again at this starting line after the same amount of time has elapsed. And this is the revival. This is the echo that Hahn saw. And the crucial thing is that this command to reverse is possible to do in a simple way in these NMR systems. You just need to essentially apply a strong pulse of radiation to the system, which causes all the spins to flip by 180 degrees. Now, this is the kind of reversal you need to do, but it's only really working on single particle dynamics of spins when the spins are not coupled. This is a picture of the data. It actually does work. You can see these huge revivals that would not be present otherwise. But nevertheless, the overall envelope of these revivals continues to decay. And so it was interesting to ask, what's the source of this decay? Well, there's various sources. There's parts of the environment you're not controlling, which are decohering the system. There's also interactions between the spins that are weak. They're the subleading effects, but they are there, and you also don't reverse them. And so they're also sort of causing things to decohere, and eventually you lose the echo. But there was a remarkable development in the 70s where various workers in that community figured out how to do what I would call a mini body echo, where they can actually effectively evolve forward and backwards in time with a mini body Hamiltonian. And the way that works is as follows. So in the top line here, I write the Hamiltonian for a pair of interacting dipoles, magnetic dipoles located at Ri and Rj, where what I've done is I've first of all applied a very strong magnetic field in the z direction. And then I've taken this Hamiltonian and I've averaged over all the terms that oscillate with that fast frequency. So in other words, you look at the dipole-dipole interaction, you can write out the form from your electrodynamics textbook. And if you write out that form and plug in what happens when you have dipoles that are precessing rapidly around the z-axis, you'll find some terms are constant in time and some terms oscillate rapidly in time. So this is an approximation. We just drop those rapidly oscillating terms. Their effects oscillate to zero, average to zero. And you're left with this very interesting looking Hamiltonian where you have sort of an XX plus YY minus 2ZZ structure times some coefficient here, which depends on the angle between the vector Ri minus Rj and the z-axis. The z-axis is the axis where you have your big magnetic field. And what these people observed is that if you imagine doing rapid rotation by 90 degrees about the x or y axis, you can take this object, which I call A, xx plus yy minus 2zz, and you can permute some of the indices around. So you can exchange, say, xx plus zz minus 2yy, or so on. And moreover, if you add these things all up, you get zero. So then if we look at our sort of, if we imagine doing some kind of Trotter evolution where we evolve with, say, H1, H2, and H3, if we're evolving with H, but interspersing those evolutions with these rapid rotations around the X or Y axis, then what we can do is we can take this pulse sequence, which is like evolving with H with rotating about X, evolving with H rotating about Y, and then evolving with H. If the leading order in delta T, you get this combined object, and because A plus B plus C is zero, you get that it's a zero. So in other words, to leading order in some kind of Trotter expansion, you can actually arrange for an effective evolution that cancels out the forward evolution. That is, you can effectively evolve with minus H and H in the same system. And of course, this is just a cartoon. This is just the sort of leading order behavior. By now, these folks engineer very sophisticated pulse sequences that enable them to more and more accurately control the details of the effective Hamiltonian that they're evolving with. Okay. So in this way, they can actually sort of go forward and backwards in time, which is pretty remarkable. And they can actually, it turns out, measure a version of this commutator. So let me explain that to you very quickly. So the idea is in the system, you have, you prepare some initial state. Your initial state is nearly maximally mixed because the temperature is very high compared to all the other scales in the problem. It's high compared to the dipole-dipole interaction, and it's high compared to the Zeeman energy from your magnetic field. But there is a very small amount of polarization in the z direction because the magnetic field is not totally zero. It's just small compared to kBt. So this epsilon is basically the Zeeman field divided by kBt. And so this is the initial density matrix. And then you can apply your time evolution, say some pulse sequence phi. Then you can rotate the total system, the whole system, by an angle phi about the z-axis. And then you can apply some other pulse sequence. And the idea here, the goal is to choose these pulses so that u and v are equal. Then you're kind of going forward and backwards or vice versa. And then based on the technology I showed you in the previous slide, it's possible to do this, at least approximately. So then if you measure the total magnetization, you get an expectation value which is proportional to this quantity, where I'm interpreting u now as a time evolution. I get IZ total at time t, this phase, IZ total at time t, and then this minus phase. And here the IZs are at time 0. And now it's a simple exercise to check that if you take a second derivative of this with respect to phi, you'll get exactly a commutator, a squared commutator of the total IZ at time t with the total IZ at time 0. Okay. So except for the fact that these are global operators and not local operators, the NMR community has been measuring out of time order correlators for 50 years. Okay, that's pretty cool, at least to me. So here's some data. Let me come to the puzzle. What I'm plotting in this figure is as a function of the time t. They call it the self time. It's just the time, effective amount of time you've evolved for. For some reason, they want to plot the square root of c. They have their own way of doing things and their own reasoning. But anyways, that's what they're plotting here, is the square root of this commutator versus time. And they get some data here. These different deltas just mean different pulse sequences. So they're just verifying that they all give you the same effective behavior over this time scale. And what they see is that if you fit these data to a power law, that the fit is to t to the 3/2. Okay, so the first question is, can we explain that? I think this is not, when they put this paper out, that they give some discussion and maybe it's diffusive. They have some thoughts, some discussion, but I think there's not a clear explanation of this physics. So I'd like to propose to you that actually we understand exactly where this comes from. Let me tell you a little bit about the system itself. It's kind of cool. Adamantane this is a molecule of adamantane. It has 16 protons that are free, that have nuclear spins that are active. And these molecules form a face-centered cubic crystal structure. And what's even more amazing is that these molecules actually tumble in place in the crystal. So they're rotating on some time scale in place in the crystal. And that has the remarkable effect of actually averaging out all the internal dipole-dipole couplings, because you think about these different pairs of internal spins, they're moving around in a circle in some kind of random way. And because their orientation relative to the z-axis is changing randomly, that interaction actually averages to 0. Meanwhile, all the interactions between one adamantane molecule and another, all the different protons, those average to some uniform value. So it's like you have 16-point dipole sources placed on the sites of a FCC crystal. So that's a pretty cool system. And they do this because the averaging, the motion of these molecules averages out a lot of imperfections. It makes it easier to see a signal. So the question for us then is, given this Hamiltonian, if we want to look at this global commutator, how do we think about this thing? Well, okay, let's expand it out. It's each of these IZ totals is the sum of local IZs, the spin operators on single sites. So we can expand everything out, and this will be a sum over a bunch of different kinds of terms where I get 4 different positions in space. And you can ask, okay, how do you calculate this thing? It's some generalized OTOC or generalized commutator. And we can give some arguments for how to think about that. I won't go into the details here, but basically what we find and what we argue is that the sort of non-diagonal terms, the terms that don't correlate the positions of one insertion with another, are essentially 0. And you can verify this numerically for small size systems. In which case, what you find is that this quantity becomes up to an overall volume in the system factor, just an integral or a sum over the region for which this local commutator is non-zero. And in D dimensions, that region has linear size VBT. That's the growth of the operator, and it's dimension D. And so then if you take the square root of this thing, you would expect in 3 dimensions, which adamantane is 3-dimensional material, you would expect 2 to the 3/2, and that's exactly what they see. So what I claim is that actually we can use this many-body chaos point of view to understand what's happening in this experiment in this material adamantane, and in principle other kinds of experiments as well. But I just focus on this one for simplicity. But the story is even more interesting than that, because actually the dipole-dipole interaction is long-ranged, right? It's a 1/r³ interaction. And it turns out that this chaos physics, this butterfly effect physics, is sensitive to the strength of to the range of interactions.
Sorry, Brian, can I just interrupt?
Please, please.
So the C was growing as TQ.
Yeah.
So why do you call it chaotic? Because I thought it should be growing exponential if there is chaos in.
Good. Yeah, this was something I kind of glossed over previously. In local systems, it doesn't really grow exponentially. I mean, if I go back to this picture, sorry, this formula here, suppose this S is like the entropy density of the system. So suppose it was just one, like you have 1 bit per thermal length.
Yeah.
Then, okay, you could have a form like this, which would still give you ballistic expansion, and there would be some exponential growth, but there's no like long time scale. There's no log S time scale for which you can use to make sense of this exponential. And in fact, if you look in local systems, you don't actually see this exponential behavior. You get a different kind of characteristic form.
Yeah.
So there isn't actually exponential there.
Okay. So, but here it's actually a global system. I mean, it's a global variable, but it's a local system. Is that what?
For this we're saying the system is local. Like, let's just imagine it has nearest neighbor interactions, and we're showing how to compute this global OTOC in terms of this local thing.
And in terms of interactions, how do we think about it? Is it all to all, or?
Yeah, that's what I was coming to next. Actually, is that it's an interesting intermediate case.
Okay. Thanks.
So when you have these power law interactions, if the interactions fall off very rapidly with distance, say sufficiently fast with distance, if the exponent alpha is large enough, then it turns out that it's essentially the same as the nearest neighbor case. And if they fall off too slowly with interaction with distance, then as you might imagine, it becomes mostly like the all-to-all case. And it turns out that we actually recently did a theory of this, where we're basing it on some kind of random circuit like a random Hamiltonian model, where there's essentially like long-range jumps. It connects to levy flights and other interesting phenomena in that vein, but there's sort of long-range power law probability jumps that can occur. And in this model, at least, you can write down a phase diagram as a function of the dimension of space and the exponent alpha. And you see if alpha is bigger than a certain value, which in 3 dimensions would be 3 plus a half, it's going to be linear, the light cone. But if it's smaller than that, then you get some intermediate behavior. You can get a power law, or you can even get log. And that would be like the case where it's exponentially growing. So this would be like all to all here in this furthest to the left region. And rather remarkably, 1 over r cubed in 3 dimensions is exactly a marginal case. It's faster than any power, but not fully exponential. And so a prediction of this theory, which is, I mean, is not a theory of this particular material exactly, but some other model that we can solve, but which has the same or similar features. A sharp prediction is that you would see faster than ballistic growth. That actually what would appear here is not t, but in fact e to the log t squared. So some particular thing that we can actually compute. And we predict this, and we think the reason why it hasn't been seen yet is because in the NMR experiment, they don't go to very long time. It's hard to do that. So there's actually a sharp prediction for many-body chaos, from many-body chaos, saying that if you can go to like a little bit longer time, you might be able to see this remarkably fast expansion of operators, which is kind of closing in on the all-to-all limit. Okay. So in the last 10 minutes or so, let me talk about one other subject, which is this discussion of optical cavities. So this is a sort of more engineered system, where now, instead of just taking a material with some active magnetic dipoles, we're going to take some collection of atoms, and we're going to put them inside an optical cavity. So a set of mirrors that tightly focus a beam of light onto this atomic ensemble, in such a way that we can enhance the atom-like coupling and see interesting physics. This is sort of a well-known general scheme. There are a lot of things you might want to do with this kind of setup with an atomic ensemble inside a cavity. Just to give you a flavor for the way the interactions could work in this case, you can think in terms of a perturbation process where there's a bunch of atomic levels, an up and a down, which are like the spin levels, and then some excited level E. And then by driving the cavity with some laser fields, you can drive transitions between, say, these low energy levels up and down and the excited state level E. And turns out to be a 4th order in perturbation theory process that you can do, which effectively flips spins from being both down to both up. And if you track the perturbation theory process, there's 2 amplitudes. There's a laser field. There's an atom-like coupling G, another coupling G, and then another laser field here. And then if you look at the energy denominators for those fourth order and perturbation theory process, there are detunings delta up, delta down, and then little delta. This little delta is called the 2-photon detuning. Anyways, you kind of get a fourth order perturbation process with 4 factors of the perturbation on the top and 3 energy denominators in the bottom and some effective interaction. So just to give you a flavor of how this sort of thing works. And so essentially you're saying you can use the light field here to couple these spins, effectively giving you some kind of, in this case, all-to-all or possibly long-ranged, at least, interaction between different spins. In particular, if I assume that these G's, which are the cavity field modes, so like the profile of the fields, if I assume that all of the spins are sitting in a region where the cavity field is pretty uniform, so they're kind of all in a one location as far as the cavity field length scale is concerned, then everything here is independent of I and J. And so I just get an overall constant times the sum over I and J. So it's just the total spin, say in the X direction squared times a constant. Okay, so you get some collective interaction between the total spin. Okay, and that's actually a nice limit, this single mode limit where everyone sits in one place in the cavity and there's only a single cavity mode. As I just said, it couples all the spins equally. Here I say SZ squared, but on the previous slide it was SX, but you can change these things by changing the setup a little bit. And this is an interesting setting because it can give rise to chaotic dynamics. There's something called a kicked top, which people have thought about and looked at and experimented a little bit. But unfortunately, it's not sort of full many-body physics. It's physics that lives in a subspace of fixed total spin, doesn't explore the many-body Hilbert space. And in particular, if you have many atoms and you initialize them in the symmetric subspace, it's basically the semi-classical limit of a collective spin on the Bloch sphere. It's like a spin S, where S is the number of atoms, essentially, or number of atoms over 2. And this is actually sort of more analogous to single particle quantum chaos, where S is playing the role of 1 over h bar. It's like the thing that makes the system quantum. So we wanted to know, okay, can we actually see many-body chaos? In fact, even this single mode setup has not really been seen in detail. I mean, there's some experiments where people have considered maybe effectively like spin 5 halves or 7 halves. You'd love to see like spin 500 or 1,000. That's really kind of getting towards the semi-classical limit. But even that's not really been done yet. That picture of the ion trap I showed you on one of the early slides, Bellinger's group did one experiment along these lines, but they just had the SX squared interaction, not the field, so it wasn't chaotic. But anyways, people are trying, and it's interesting. But if we want to specifically see many-body chaos, we need something more complicated. So there's been a lot of proposals in the literature about how to do this. But none of them have been successfully realized yet, at least not at an interesting scale. And so we had a new idea, which is really a question. Can we get a fast scrambler by coupling a local scrambler to a single cavity mode? So, essentially what's hard is to do this kind of all-to-all addressing where everyone talks to everyone, but with a different random coefficient. Like if you're thinking like SYK model or some Heisenberg, all-to-all Heisenberg model, you need all this kind of, all these different random numbers, and that's hard to get. But maybe if we had just the single cavity field shown here, plus like local chaos, maybe that would be enough to give you fast scrambling. And what we show in this paper is that the answer to that question is yes, this is sufficient. So you just take like a chaotic spin chain, like the thing I showed you on one of the early slides, and you couple it to this uniform cavity mode, which is here approximated by just a total SZ squared interaction, with a certain particular normalization with a number of spins, maybe a kind of funny normalization. You might think that you would want 1 over n here, but actually you need 1 over square root of n in order to get a non-trivial effect. And we claim that with this, then this Hamiltonian H is actually a fast scrambler. It scrambles in time log n. The way we know that with high confidence is that we can consider a random circuit model where the evolution is composed of 2 pieces. One piece is like just a local random rotation. It's random in space across qubits and also in time. So this blue box is different from that one. It's different from that one, it's different from that one, etc. And then you intersperse that, interleave it with this total SZ squared evolution, which is non-random and just fixed. But with this particular normalization of 1 over square root of n and the coefficient g, which sets the strength. And we can actually analyze this situation analytically it's a random circuit, we can derive some master equation, some probabilities, and show rigorously, that the out-of-time order correlator in this model grows exponentially with time at a rate proportional to g squared at small g. Okay, and there's some saturation, and we can verify everything you want. So at least in this model, we can prove analytically that with this particular 1/square root of n normalization, you get the fast scrambling. Now, you might wonder, whether this 1/square root of n is maybe an artifact of the randomness. We thought that as well, perhaps, but it turns out there's actually a bound due to Andy Lucas and his student that shows it cannot be smaller. It cannot scale within like 1/n, for example. That would not be enough to give you chaos just rigorously. And so it seems like this 1/square root of n is actually crucial. And then, okay, in fact, this random circuit model is not impossible to imagine in implementing. It's not necessarily unphysical. But if we do want to have a Hamiltonian, we can look back at this, say, spin chain case. So here I show you like a spin chain, similar to the one I showed in the first slide. I've dropped the extra longitudinal field and just added this total SZ coupling, total SZ squared coupling. And that turns out to be enough to still make it chaotic, even though the first two terms by themselves would not be, and to also spread this perturbation very rapidly. So here's the out-of-time order correlator. In the local case, you see a pretty clear light cone. This is now a small size system because we're doing exact diagonalization, but it's still pretty convincing. And then instead, if you look at the non-local case, you see that there's sort of a light cone at very early time, but then it quickly sort of bottoms out and you get these contours of constant out-of-time order correlator that are essentially flat as a function of space, which means everyone's growing at the same rate. Okay. So we have this, particular spin model, which maybe is experimentally reasonable, whatever. And we also have evidence there that with the 1/square root of n, you have chaos and you have the fast scrambling behavior. Okay. So that's the answer to the question being yes. Okay, so I think with that, I want to go ahead and wrap up and open up to more questions. So let me just say that I hope I convinced you that there's still a lot of mysteries in QED. Maybe that's not a controversial statement. I mean, QED is super interesting. But there's actually quite a few unexplained phenomena, I think. For example, I argued that there's really decades-old phenomena in MR experiments that actually probe many-body chaos. And I sketched for you, I didn't discuss in detail, but I sketched a theory that predicts some remarkable signatures of this dipole coupling, for example, that you would have this super ballistic and in fact super polynomially fast growth of perturbations. In fact, it's kind of remarkable. You normally think that you have a good notion of decoupling here. You can ignore the speed of light. It's very, everything happening in the lab is very slow compared to the speed of light. But it actually seems like because the interaction is so long ranged, that you need to re-include the speed of light into your description to have a finite velocity of information propagation. So that's pretty remarkable phenomenon. And we hope that will be able to be seen in experiment relatively soon. And more generally, I think, I've been learning a lot from the NMR community, and I think there's a lot more to learn from them as well. A lot of cool stuff there. And then the other example I told you about was a particularly simple, from an experimental point of view, fast scrambler. We would call it the simplest, I think, because it really has a very small number of ingredients. You don't need a lot of random couplings. You don't need a lot of engineered structure in the interactions. Just this one global field plus some local interactions is enough. In fact, in the random circuit model, you don't even need local interactions. You just need a random local field. And we're hopeful that this kind of development will help push the field a little bit further and let us really access fast scrambling in the lab very soon. This is, of course, one of the stepping stones to looking at quantum gravity in the lab itself, which is a long-standing dream that many of us have. For the NMR problem, we're hoping to finish our paper soon. There's actually interesting connections to like large N models. I told you that you have these 16-point dipole sources effectively on this FCC structure. And so that's actually not unlike the random Hamiltonian models that we considered, where you have like a large number of qubits on each site and they interact in some random way. So maybe we can actually make a concrete quantitative connection to some large N random circuit models. That would be really cool. It would give us control over the experimental problem, for example. And then for the simple scrambler, there's lots of questions there as well. What happens at finite temperature, for example? It's very interesting. You know, could we reach a regime where you actually have maximal scrambling? The semi-classical limit's also quite interesting, where these spins on the spin chain are not spin a half, but some spin s. Then there's interesting questions about how the semi-classical limit locally crosses over to the sort of fully quantum limit. And this is also interesting because that's what's easiest for them to do an experiment right now. So I think there's a lot of places where you can get your hands dirty if you're interested in this physics right now. And I'll thank you just by advertising in this time where connections are difficult. Some other work in my group, there's several postdocs, Xiaokai and Chris, and students, Shibayan, Gong, and Mike, who are all doing things related to what I talked about today. And you know, if you're interested in any of them, I encourage you to reach out to them. So thank you very much.
Let's thank Brian, maybe unmute ourselves and thank Brian for a wonderful talk. And since Brian has been sticking to time very well, we have some time for questions and discussions.
Can I ask?
Yeah, sure. Go ahead.
Yeah. Brian, thanks for a very interesting talk. I have a kind of a general question, I think. Suppose you have only local interactions, but your operators or observables are, kind of global variables, like for example, just the total spin of, let's say, half of a spin chain.
Yeah.
So is there any reason to expect that you cannot have fast, scrambling in this situation?
I'm concerned. I'm not sure what you. I don't know exactly what you mean by scrambling or fast scrambling here.
So let me just clarify. Just an exponential growth of OTOCs.
Yeah, this is a sticky issue. It's not clear that it's impossible.
Yeah.
But no one has shown it. In fact, I mean, whenever you look, you see that it's not there so far.
But okay.
But
so I mean, we have seen such things in Floquet spin systems. So, but it's not also clear that this is something which is only there for non-integrable systems. So I don't know.
Yeah. So good. Yeah, you're making a lot of good points. I mean, so one thing maybe I'll just go back to this picture. So this picture here, like if you look in this sort of what I call early growth region here,
yeah,
then you often find some kind of rapid growth with time, which is not necessarily exponential, but like some stretch exponential. And that you can see in all kinds of systems. So like you'll see one value for holographic systems that would just be linear in T. You see a different value for spin chains that are chaotic, a different value for free fermions, a different value for Heisenberg. So there's a lot of richness there, but you will see this rapid growth. That's very common. And then if the system is not chaotic, usually what you'll see is that it then drops back off again. So instead of going to this plateau, it kind of dies away. So we should really be careful when we say that like just seeing this early growth is really chaos. It's not by itself, or it can be confused with other effects. And you really need to see that the saturation is really kind of the other key feature.
Yeah.
And so we have an ansatz, so a framework that we propose, which seems to capture all the examples I know about. Like there's basically another degree of freedom, another variable that quantifies the commutator. And that seems to match all the cases that we know about, including like free particle cases and other kind of cases. And in particular, what you find is that the generic behavior for a local system seems to be that it's not exponential, but actually has some diffusive broadening of this front. So the front expands ballistically, but also gets broader, like square root of time in 1D. It's possible we conjecture, my student Shibayan and I had a paper with this recently, we conjecture that maybe if you go way out ahead on the front, it could be exponential again very far out here, if you define it suitably. That's not clear. It's also possible that in like higher dimensions, maybe the fluctuations are not important enough. So maybe this is getting into the weeds too much, but so like in 1D, it's essentially like you have this ballistic motion plus random walk, and that gives you diffusion. In higher dimensions, it's a random surface growth problem. At least that's the simplest version of it. And if you have sufficiently high dimension, there could be a trivial fixed point of that problem where the surface is not roughened, in which case you could still have an exponent. But that's also highly speculative. So that's kind of what I know about the subject at this stage. I'd love to have an example or to understand these flow K examples that you're speaking about if they show something along these lines.
Yeah. Okay, thanks.
So
Brian?
Ayan had a question. Yeah, you can go ahead and ask your question, Ayan.
Yeah, thanks, Prabha. So I don't understand why the circuit has anything to do with quantum gravity. It's great that it is scrambling fast, but and what should I learn about quantum gravity from that circuit?
You mean this circuit here, for example?
No. The circuit in your yeah, this circuit, random circuit model.
Yeah.
Yes.
Yeah, it has nothing to do with quantum gravity. Well, it has very little to do with quantum gravity. So this is really about a more primitive goal, which is to just see fast scrambling in the lab. And
yeah,
and that's, I mean, you know, I can try to defend a little bit more strongly than that. Like maybe there's interesting connections between random circuits, like JT gravity is like a random matrix ensemble. Some other random circuits can do some interesting things that are not totally unlike gravitational phenomenon. But for me, that's an interesting conversation, but I'm not trying to really defend that point of view here. I just want to say this is something which is a fast scrambler. And it's not gravity, but we don't even have fast scrambling yet, let alone, you know, SYK or N equals 4 super Yang mills or whatever. So this is kind of a first step that we need to master before we can hope to see that kind of physics in the lab. That's my perspective.
Yeah, and also this picture that we have so far in quantum gravity is mostly Euclidean, that we are sort of connecting it to random average of some random matrix ensembles. So well, we also have sort of a Lorentzian picture perhaps through this mod square of so what kind of experiments that you would like to do? Suppose you had something like that. What you would like to do to learn about quantum gravity from
if we actually had, like, suppose I had one of these, you know, like SYK or something.
Yes.
I mean, you know, the simplest thing. I mean, we can just take a relatively simple example like BFSS, right? You know, there's this incredible work in the Monte Carlo community where they're like trying to measure the entropy essentially of this thing, including the 1/n corrections as a function of temperature to like match to gravity. And that's like very hard for them to do. But this is the kind of thing you could do pretty easily on some quantum hardware if you had this system, you know, simulated in your qubits. And so something as simple as that, just like what's the entropy as a function of temperature, which tells us about the black hole entropy and about quantum corrections to it, or weak coupling corrections to the strong coupling answer. That's already interesting and already something that you could imagine learning about non-perturbatively using a quantum simulator that had your favorite matrix model loaded into it. There are other questions, you know, time scales for entanglement dynamics that are hard to ask it and answer at finite n. So for example, this thing I mentioned here about the fact that this profile is broadened as a function of time in one dimension, like square root of time. We think that this effect should be visible in gravity as well, and it must be a quantum fluctuation effect. It's a finite n effect. But no one has so far been able to reliably compute it. And, you know, I have some hand waving and some guesses and some sort of quasi theories, but nothing very reliable yet. And so this is, you know, this is an example where something you could actually try to just measure. You can go out and just measure and see if the broadening is there, and then hopefully understand from the measurements and related quantities that you looked at in the system, you know, how to understand the physics of this broadening in this gravity system. You know, what kind of fluctuation is it, or what's the source of it? What can enhance it? What can suppress it? You can also look for, other systems that have maximal scrambling. So start from SYK and add perturbations and try to look, try to search through the landscape of models to see, if you can sparsify the spectrum while keeping maximal scrambling. These are all, just some sampling of directions that you could go. And I think you definitely could learn something about, just the thermodynamics. You could learn about 4-point functions, scattering processes. You could learn about chaos, what kind of models are holographic, what kind of models are not. There's a whole dream list of things. But first we need at least fast scrambling in the lab. So that's what this is about.
Okay.
Maybe we have time for one more question. Perhaps I shall ask one, if no one else is wanting to. So I actually had a question about this random circuit model. So
yeah,
the commonly studied random circuit model is one where the U2 is actually bipartite interactions, really, in the sense of just 2 qubit or two qubit terms maybe, and the
yes.
U1 is local in the true sense of single quantum systems. But your U1 actually is a nearest neighbor Hamiltonian, right? The spin chain. Is that, or did I misunderstand?
Yeah. Sorry, I was slightly unclear about this. So this random circuit model actually is just single site unitaries.
I see. Okay.
So I mean, to be clear, like I'm sure it will work even if you have the 2-site coupling as well. Like that will only help things, but it turns out that that's a little bit harder to analyze. And this is already sufficient to give you the many-body chaos. So that's why we looked at this limit. But for this model here, you do have also the local near neighbor coupling.
Okay. Yeah. So that's what I was confused about. So then in the many-body model, do you really need the all-to-all interaction, or can you do with something fewer and still get fast enough scrambling?
I'm not sure what you mean by fewer exactly. You can certainly consider other things. So like, for example, a postdoc of mine, Greg Benson, did some nice work where with the late Steve Gubser and Monica Schleier-Smith and others, where they proposed this interesting model where you have a spin chain where you have like nearest neighbor and then like second neighbor and fourth neighbor and eighth neighbor interactions in some like exponentially growing sequence. And I'm not sure if you consider that more or less than this. Like maybe there are fewer interaction terms, but they're individually stronger.
I see.
And that can also, with the right scaling, give you fast scrambling.
Okay.
So there's a lot of different things you could try, and it's a bit subjective, or depends on the details of the experiment or what you're hoping to get out of it. But this seems like a particularly simple thing that actually they can do pretty soon, we think.
Can I just ask a final question, maybe, Prabha? Sorry.
Yeah, sure. Go ahead.
Actually, this because you pointed out this random circuit model, Brian, isn't the kick top exactly of that kind, except that there's no square root n scaling there?
Yeah. So for the kick top, we would drop the j.
So it's just nearest neighbor, right? I mean.
No, I mean in the next slide. Your random circuit model. Yeah,
this one.
Yeah.
Sorry, the kick top is this where we enforce that the random field. Well, if we fix the field to be the same in space and time.
Right. Okay.
And we would need the normalization to be 1/n instead of 1/square root of n.
Okay. So here it's a random. I see. So that's why you won't have a collective variable.
That's right, exactly. So in that limit where the field is the same on every site, then it's restricted to this symmetric subspace, or it's restricted to fixed total spin subspace.
Yeah.
And that's why I call it a collective variable there. You don't have the many-body physics.
Yeah, thank you.
Nice. If there are no more questions, let's thank Brian again. Thanks, Brian,
for
a wonderful talk. Yeah. And if our next speaker is ready, Shira Chapman.
Yeah, I'm ready.
Yeah. Hey, Shira. So welcome to the Dual Mysteries Conference again. And our next speaker is going to be Shira Chapman from the University of Amsterdam. And I hand over the floor to her now.
Right, so let me start by sharing my screen. Right, so just a second. So can you see the screen well?
Yes, we can.
And the cursor as well?
Yes, yes, indeed. Yeah.
Excellent. All right. So let me start. So hi, everyone. I would like to start by thanking the organizers for inviting me to give this talk here. What I'm going to talk about is a paper which we wrote together with Kostas Bakas, Dongsheng Ge, and Giuseppe Policastro. In this paper, we were trying to study some universal properties of energy reflection and transmission from what is known as conformal interfaces using a very simple holographic toy model. Now, before I start, I wanted to say that since it's the first time I'm giving this talk, and it would really help me gauge the speed if some people would agree to have their cameras on. Of course, only if people feel comfortable, but yeah, I like looking at faces. All right. Okay, so that's the overview of my talk. I'm going to start by giving an overview of conformal interfaces, what they are in general, and in particular, what are the special properties in 2 dimensions. The second part of the talk is going to be focusing on describing the simple toy holographic model, which we use to study those interfaces. That's the thin brain model. We've heard a number of talks about similar things in this conference. And then I will describe our results about energy reflection and transmission in holography. All right, so first thing first, I'm going to start with talking a little bit in general about 2-dimensional conformal interfaces. So first thing is, what are interfaces? Interfaces are codimension 1 extended objects which split the system into 2. In particular, if I'm thinking about a 3+1 dimensional system, in every specific time, these will be surfaces which split the system into 2. Or when talking about 2-dimensional systems, I'm going to think about an impurity in the middle of a chain, which splits, say, the line or the chain into 2. And as usual, if I add more symmetry, I can say more. So I will focus on the special case of conformal interfaces, which separate 2 critical systems, 2 CFTs, and preserve a large subgroup of the conformal symmetries. So specifically in 2D, these are impurities, which preserve 1 out of the 2 copies of the Virasoro algebra. So going back to the picture that we are all used to, adding back the time direction, I have a CFT living on one side, CFT left, and another CFT living on the right side. And the interface lies along the time direction. And so the interfaces are going to be conformal if they preserve a certain superposition of the Virasoro generators, which do not displace the interface, and that's 1 copy of the Virasoro. Now, it turns out that when the interfaces are conformal, due to the translation invariance along the time direction, no energy accumulates inside the defect. So whatever I send in the direction of an interface of this kind is either transmitted or reflected, but nothing gets like kind of swollen inside the defect. And that basically amounts to a matching condition on the stress tensor, the continuity of TXT. And finally, for those of you who have experience working in defect CFTs in higher dimensions, you know that the spectrum of operators contains an operator in the defect, a primary operator associated with the defect, which is the displacement, whose role is that when we insert it inside correlation function, it moves the defect a little bit. So it turns out that in 2D, the displacement operator is a simple linear combination of components of the stress tensor. That's something special about 2D. Now, as usual, conformal symmetry helps, but we have less than we are used to, and so it does less for us. But still, 2 and 3 point functions of the stress tensor are fixed by the conformal symmetries. So in particular, 2 point function of the stress tensor on the left separately or on the right separately are fixed by the left and right central charges associated to the two CFTs. But now there is also a new coefficient which characterizes the left-right correlations, and that's going to be the star of the play. That's this guy, C left-right, which appears in the 2 point function of one stress tensor on the left and another one on the right. Another thing which also happens for boundaries is that we have some kind of mirroring effect, so there will be correlations of T and T bar. Yeah, the 3 point functions of the stress tensor, I didn't write them here, but they are also completely fixed in terms of these exact 3 coefficients, while other higher point functions are not. They depend on the details. All right, so what is so special about energy reflection and transmission in two-dimensional conformal interfaces? The thing that is special is that they are universal. So let's imagine a scattering experiment where I send an incident wave in the direction of the interface, and I have a part of it which is reflected and another part which is transmitted. I'm going to define the transmission coefficient as the ratio of transmitted energy over the incident energy, and the reflection coefficient as the ratio of the reflected energy over the incident energy. Now, generically, these two coefficients are different depending on which side I'm conducting the experiment. So if I'm sending my wave from the left side, I will have a left reflection and transmission coefficient, while if I send it from the right, I will have a right reflection and transmission coefficient. But the thing that is, in fact, very special about those interfaces is that the scattering is universal. So the amount of scattered and reflected energy is completely independent of the details of the incoming excitation. So no matter which kind of superposition of operators I construct, which kind of wave packet I make from them, etc., nothing actually depends. The amount of the total energy reflected and transmitted it does not depend on those details. All right, and it turns out that these reflection and transmissions are completely fixed in terms of this like 2 point function C left coefficient C left right, which appeared before in the 2 point function of the stress tensor. So in particular, the transmission for a wave coming from the left is going to be the ratio between C left right and the central charge of the left. And the transmission coefficient is going to be the ratio of the C left right and the central charge from the right. And naturally, the reflection is simply 1 minus the transmission. Now, the positivity of the energy, both reflected and transmitted, or more formally, that's the Anneck condition on the null line at null infinity, basically tells us that for all these quantities to be positive, I need C left right to be bounded between 0 and the minimum of the two central charges. And when I translate this back to talking about transmission and reflection, it tells me that the transmission is bounded by 0 and the minimum of 1 and the ratio of the central charges. And that's actually quite intuitive. So it just means that if I'm moving from a CFT with more central charge, so more degrees of freedom, to a CFT with less degrees of freedom, I can't actually fully transmit because I don't have degrees of freedom to carry the perturbation away. I can only transmit as much as the ratio of the number of degrees of freedom on the two sides. It may be a bit of a simplified picture, but just to have an intuition. So keep in mind those bounds on the transmission and reflection. They will come back later on. All right. Any questions about those? Yeah, about the 2D interfaces.
Are the phases also universal?
Not that I know of. Not that I know of. All right. Okay. So I'm going to now look at a simple holographic model in which these things can be evaluated. This model, you heard about it quite a bit at this conference. And this model is basically a thin brain lying inside ADS3. So the idea is that we have under the right CFT an ADS bulk, and under the left CFT also an ADS bulk, and these two bulks are patched together along an ADS2 brain. The model basically consists of an action with Einstein gravity on the left, Einstein gravity on the right. It's a bottom-up approach with two different cosmological constants to lead to two different central charges, and the brain action, which depends on attention and the induced metric along the brain. Now, we know that we can solve Einstein equation in the left and right patches and get, well, the usual thing, simply ADS3 on the left and ADS3 on the right. And in order to determine the position of the brain, one has to solve Israel matching condition to find the location of the brain. So these are simply continuity of the induced metric and the fact that the jump in the extrinsic curvature is fixed by the tension of the brain. All right, so the equations of motion, so the Israel matching conditions have stable solutions with a thin ADS2 brain, as long as the tension is bounded between two different values, the sum of the inverse central charges and their difference. And in this case, indeed, the solution consists of two patches of ADS3 connected with an ADS2 brain in the middle. And the angles, so it's actually a bit more than half ADS3 and a bit more than half ADS3, and the angles are fixed by the various parameters, so by the cosmological constants and the tension. Right, and finally, I should say that a number of different things have been computed in this model. In particular, the additional entropy associated with the presence of the defect, that's the defect friend of the boundary entropy, has been computed and is fixed by the tension. So why would we want to evaluate energy reflection and transmission in this thin brain model? So the reasons are twofold. The first thing is that understanding we would like to understand better the energy reflection and transmission in strongly coupled models with large central charges. In particular, we would like to see if this tells us something more. Does this improve on the reflection and transmission bound, etc.? Can we understand these systems better? But another reason is that this thin brain model actually appears a lot, especially recently in studies of the page curve of black hole evaporation, while actually we don't know that much about it. I mean, we know the equivalent of the boundary entropy, but we don't know anything about correlation functions. We don't know how to solve various things on this background. And so basically understanding the reflection and transmission amounts to starting to understand this model better. Yeah, and this you've heard a number of talks, indeed by Raju, and perhaps the talk of Pratik that comes after my talk. In these models, which try to depict black hole evaporation with a doubly holographic dual, the black hole actually lives on a brain, is effectively traced on a brain exactly of this type. All right, so now to our calculation. So what we wanted to do was to find the reflection and transmission in this holographic model. And I'm going to start by telling you the final result and only after the derivation. So what we found was that the transmission coefficient depends monotonically on the tension. So basically is given by this expression, and this you can kind of understand. This means that if the tension is higher, it kind of blocks more, it's harder to move the brain in the bulk, and so less stuff gets transmitted to the other side. We find that in this case, the transmission is fixed by the tension, And that's also true for the boundary entropy in this model, but this is only because our model has a single parameter in addition to the central charges that is not expected to be generic. So generically, the expectation is that boundary entropy and transmission are two completely different things. So there are, of course, many examples. One of the examples would be, for example, to think about Chern-Simons interfaces, which are dual to Chern-Simons theories in the bulk, where the boundary conditions on the brain are able to change the boundary entropy, but the transmission is always one because this model is topological. So we should keep in mind that this is a little bit like A and C central charges in Einstein gravity, that they accidentally are the same because we don't have that many parameters, but this is not always the case. Right, and then if we plug the bounds on the tension, which we're required to have a stable solution, we find bounds on the transport. And these bounds are exactly matching, the upper bound is exactly matching what we find from ANEC, which is great. It's a consistency check of the calculation. The lower bound is stronger, so it's given by this expression, and I will say something about it in a second. So let's think a little bit about the bounds. So you remember that the upper bound told me that I couldn't fully transmit from a lower central charge to a higher central charge. That remains. If I want to have complete transmission from both sides, so this is like one in both, this can only happen when I have equal central charges and for a tensionless string. So this upper limit is obtained by the tensionless string. And that's the holographic equivalent of a topological interface. Now, the opposite limit of total reflection from one side can only be obtained if the ratio of the central charges is vanishing. So for example, if C right over C left goes to 0. And that means that if I want to have complete reflection, I have to completely deplete one of the CFTs of degrees of freedom relative to the other one. That's kind of a BCFT limit. And that's very different from what happens in generic defect CFTs, because usually there is no problem to put such boundary conditions in such a way that the two sides don't talk. But somehow this brain in the bulk forces the two sides to talk as long as I don't like completely kill the other side. All right, so that's our result. And now I will tell you a little bit how it's derived. So what we did was that we looked for bulk solutions which correspond to this scattering experiment. So we wanted to turn on a stress tensor on the left part and a stress tensor on the right part, which would represent the left and right moving waves with some small amplitude. We were working perturbatively in this epsilon. And so basically, we have an incident wave with a certain amplitude and a reflected wave which goes left with relative energy left reflection, and that's the transmission coefficients. And those waves have frequency omega. We will see that one depiction of the universality is that the amount of energy reflected and transmission is not going to depend on omega. So omega is going to consistently cancel from the calculation. Now, what we have to do is we have to solve three things. We have to solve for the left bulk, we have to solve for the right bulk, and we have to patch them together along the ADS2 brain. So the left and right bulk are actually given very simply by these Banyados type solutions, which we know completely fixed by the stress tensor. The metric is at 0th order in a Fefferman-Graham expansion is the flat ADS metric. The second order is given by the stress tensor, and the fourth order is completely fixed again by the stress tensor squared, and there are no additional corrections. That's something special to three-dimensional bulk. And so the next thing to do is that we need to find actually the location of the brain and how the brain is perturbed. So without the metric perturbation, without the stress tensor addition, we know that the brains are simply matched with an angle theta left and theta right, and these two brains are identified. I'm just drawing them apart, yeah, so that we can see things better, but the point is that when I hit the brain, I exit on the other side. And with the perturbation, the brains get perturbed, and we want to find the shape of this perturbation. So I'm going to use coordinates tau left, x left, z left on the left. and tau right, z right, x right on the right, and some coordinates inside the brain, tau and z. And so the unknowns of the problem are how to identify the two sides. So in particular, what is the relation between z left and z when I hit the brain and to z right? Of course, only the difference would matter. And the time. So how do the times match when crossing the brain? And this I'm going to parameterize by unknown functions. Zeta represents the matching of the values of z between the outside and the brain, and lambda, the matching of the time. And of course, I mean, these coordinates that I put on the brain, they are just like some kind of gauge choice. So what really matters is how I jump in z when moving between the right and the left, and how I jump in the time when moving between the left and the right, and the location of the brain. So I'm going to parameterize the location of the brain by x of the brain is a function of z and t. All the functions are simply exponentials with this frequency to the I omega t, and unknown functions of z, which is what I'm looking for. So 4 functions, zeta, lambda, and the 2 deltas. All right. So now I want to solve the Israel matching conditions to determine what those functions are, what those 4 unknowns are. Naively, it may look as if those are 6 equations, but actually 2 of those equations are dependent due to Gauss-Kodazzi. And so I actually only have 4 equations to solve for those 4 unknown functions, which is great. I, R, and T are basically encoding what happens with the incoming wave, the reflected and the transmitted wave. And you remember that all those functions were multiplied by an e to the I omega t. So actually I have a bit of a weird phenomena here, which is that all of the functions contain things like e to the I omega t, things like minus sine theta z. And that's a bit awkward because these are propagations which move at superluminal speeds. And so at some point we were quite confused about that. But then we understood that that's not really that something is moving. It's exactly what happens with a wave which hits an oblique seashore. So if the wave is going exactly or almost exactly in the direction of the shore, the wave fronts are going to hit instantaneously, or if I just deflect a little bit, they will hit very, very fast. So it's just the depiction of the bulk waves on the brain, but there's nothing wrong with that. All right, so solutions. So you remember I had 4 functions to understand the matching of the brain. Let's start by turning off from the previous slide the sources. So I'm going to turn off I, R, and T and just solve the homogeneous part of the equations. So if I solve the homogeneous part of the equations, I'm going to get 2 integration constants to do with the 3 equations for the matching, and 1 additional constant, which is to do with the difference delta left minus delta right, so with the displacement. That constant is actually the source for the displacement operator. It tells me when I go to the boundary, what is the how much the brain is displaced. And in particular, when I'm trying to look for homogeneous solutions, I'm going to require that when I arrive to the boundary, everything is trivial. So I want a straight boundary when I reach z equals 0, and I want the matching of time from the 2 sides to be trivial, etc. So that's simply going to set to 0 all these constants. The next step is to add back the perturbation, so to look at the non-homogeneous solution, and this basically adds a back dependence on those I, R, and T. And now again, I impose basically the same boundary conditions. So I still want a flat defect when I reach the boundary, and I want the matching. I don't want a jump in time when I go from the left to the right CFT, etc. And so this gives me 4 constraints on the 4 functions, and I'm able to solve for the integration constants, for the 3 integration constants, and get 1 constraint, which is that reflection plus transmission equals 1, which is great. That's what we would have wanted. That's a bit of a side comment to say that with those choices, if I plug them back in my functions, all the functions expand to order z cube near the boundary, and that has exactly the right dimension to be the vev of the displacement. So the whatever remains after this expansion, the constant has dimension. It's expansion of length scales, and so has dimension 2, which is what you would expect to be the vev of a displacement. All right, but there is still something missing, because this all seems completely 100% consistent with whatever reflection and transmission that I want. So what is missing? And so it turns out that the one thing that is actually missing is that I need to put a boundary condition in the IR. Normally, I would not want an outgoing wave that come out of the Poincare horizon. But it's a bit subtle, because I don't quite know immediately what to turn off. So for example, let's look at one of those functions, delta. The functions have outgoing and incoming waves and a bunch of terrible superluminal modes. So what should I actually exactly turn off? And the answer to that is that I should be looking at some kind of gauge invariant quantity that is attached to the brane and that doesn't depend separately on parameterizations of the left and right compared to the brane coordinate. And that quantity turns out to be the traceless part of the extrinsic curvature. The traceless part of the extrinsic curvature is such that doesn't depend on the separate parameterization of the left and right copy, which is pure gauge. And in this quantity, all the superluminal waves cancel, and I'm left with simply one outgoing wave and one incoming wave. The outgoing wave is associated with the coefficient A+, and so I have to set A+ to 0. But you remember that from the solution, A+ had an expression in terms of reflection and transmission, and setting it to 0 then fixes the transmission to a particular function of the angles of the brane, unperturbed, and translated back to the tension gives me this answer, which we looked at earlier.
Shira, can I ask something?
Absolutely.
So I was just thinking of this counting that you had for this, the number of Israel junction conditions, whereas you had only 4 functions to solve for, right? So you needed something more, and then this particular infrared condition was enough to determine it completely, or I just want to know the counting.
Yeah, no, that's a very good question. So I think maybe I mixed 2 things up, which is the number of equations and the number of boundary conditions. So yeah, somehow my computer has been kind of slow, so go back in slides is a really serious challenge. Just a second. Right. So the one question is, how many equations do I have for how many unknown functions? This is what I said about the Israel condition, that since this is a 2-dimensional induced metric and a 2-dimensional extrinsic curvature associated with the surface, it naively looks as if I have 6 equations. But these equations are redundant because of the fact that the brane is basically ADS2. So I have a Gauss-Kudats equation on the brane. So then I do have 4 functions and 4 equations, and that's great, and I can solve. Then the next thing is to do with the boundary conditions. Now, since these equations are coupled, since these equations are coupled, they basically give you, if you start plugging them one inside the other, you get one second-order differential equation. And so you have 2 integration constants associated with these 3 functions and another one associated with the last. So just 3 integration constants because of the way the equations are. And then when you impose the boundary conditions, of course, you have 4 boundary conditions, you get 3 solutions for the integration constant and 1 constraint, which is this R plus T equals 1. But that's not enough to fix. That's completely consistent without fixing what the reflection and transmission are in terms of the tension. So that was the point of the IR condition, was to impose an additional constraint after having solved for all the integration constants, to put an additional constraint which ties the transmission to the tension.
Oh, okay, thank you. Yes.
I'm sorry, I don't know. It's moving somewhat slowly. All right, so let me summarize. So I've told you that energy reflection and transmission are universal in holographic interfaces. And in particular, we found that in the thin brain model, the transmission is fixed by the tension. Now, I told you that this, in the case of the thin brain model, actually tells me that there is a relation between the boundary entropy and the energy transmission, but that relation is not expected to be generic based on various examples that we know. In general, it's interesting to understand what's the relation between energy and entropy transfer through this kind of brains, especially interesting in the context of this, the page curve of black hole evaporation, all these stories which use exactly a brain like that. And one thing that I haven't told you, so you saw that the frequency did not stay in the calculation. So the transmission and reflection did not depend on the frequency. And that's one aspect of universality. But of course, it's not the whole story. Because I just shot stress tensor waves at the brain, and I might want to perturb the brain with different operators or wave packets constructed from different operators. And so the next step to say prove universality in this model is to, although it has been proven in CFTs, is to try and shoot other things at the brain and see what happens. And of course, it's also very interesting to look for models in which the boundary entropy and the tension are not tied. There are various directions to go. So that's it. There's lots to explore. And yeah, thanks for listening.
Let's thank Shira for a lovely talk. Yes, she finished on time, so we have time for a couple of questions. If you have a question, you could either type it in the chat or just unmute and ask yourself.
Yeah, I see one question.
Yeah, Ayan, you could just ask your question. Yeah.
Yeah, so in this context of this, I think you're talking of this page curve calculation. So what exactly you mean here by entropy transfer in that context?
Yeah, that's a very bad choice of words. The next time I give this slide, it's not going to be phrased this way. What I mean is information transfer. It's basically that, okay, I will tell you, the thing is like, if you think about the model, specifically the model in Van Ramstong's paper, the one that has the black hole living on a brain and anchored at two CFTs on the two sides, this model is in thermal equilibrium, so energy is not moving. And so you have a hint that you transfer information between the, I don't know, the buff and the black hole, although you are not moving energy. And so it's interesting to, you know, to understand the interplay. How is there anything universal, for example, in information transfer? How is it fixed by correlation functions, etc.? Is there any relation in certain cases to the energy transfer? Yeah, so that's what I meant, but it will be phrased differently the next time. Yeah.
Okay, so you want to look for something analogous to a first law there or something?
Yeah, maybe something along these lines. Mm-hmm.
Mm-hmm. Yes.
Are there any other questions? If not, let's thank Shira again. And can I request our next speaker, Pratik? He's here.
Yeah, just a second. Sorry. Oh, somehow, do I have sharing rights?
Yes, you should. You're also co-host, I think. So
Sorry, there's some problem. Let me just fix that.
Are you trying to share from your iPad or something?
Yeah, yeah.
Okay, yeah.
Is
That
that
thing is
problem?
not a no. That is not a co-host.
Oh, okay. Do you have to make me host for that?
Yeah, it should work now. Oh, I don't see your iPad anymore. I think it disconnected.
Yeah, no,
Yeah.
I'm trying it now. Yeah, I'm trying it now. No, it still didn't work. I think I'm still co-host, right? Or
Yeah. You are co-host, but I don't see your iPad on the participants list.
oh no, I'm just like sharing screen. I have not joined the call separately from it.
Okay.
I think if you make me host, then it'll work.
Actually, only one person can be the host, actually.
Oh, I see.
There should not be an
Oh,
issue with the co-host. Maybe, I don't know, with the iPad, it might be a bit tricky.
Let me, okay. Ideally, I do that. Let me just try to share by AirPlay or something. Does this work now? Okay. Can you see my screen and hear me?
Yes.
Okay.
Yes.
Yeah, thanks.
Okay, our next speaker is Pratik Rath from the University of California at Berkeley, and hand over the floor to Pratik now. Go ahead, Pratik.
Okay. Thank you. Thank you so much for this invitation, firstly. And let me congratulate IIT Madras on having such a lovely conference. So congrats to the organizers. And let me also thank you separately for a personal thing, which is like I have an annual trip to India every year. Clearly this year it wasn't possible. So at least this way I'm getting to visit virtually. So thank you so much for that. So this, the work that I'm going to talk about today is what we call the page curve for reflected entropy. And I started this work when I was at Berkeley. Now I've moved to Santa Barbara, and this is still to appear, but hopefully it should appear soon. And this is work in progress with my collaborators, Chris Akers at MIT and Tom Faulkner and Simon Lin at UIUC. So let me get started with some motivation and background, just to get everyone on the same page. So let's say you had a density matrix on some subregions AB. This is some mixed density matrix, and you could purify this state in many different ways. It turns out there's one canonical way of purifying it, which is just take the square root of the state of this density matrix and think of it as a state. So the square root is an operator which lives in the Hilbert space, which is end of HAB, which is the set of operators that act on the Hilbert space HAB, where the inner product is defined by the trace in this way. And as is well known, this is isomorphic to basically two copies of states living on AB. So you have HA tensor HP, but also HA prime tensor HP prime, which are like their doubled versions. That's an abstract way of saying something that's pretty familiar to people in a different context, which is basically if you had the thermal state, if you started with rho AB being the thermal state, then we're pretty familiar with the thermofield double, which is essentially just taking the same state, taking the square root of the coefficients and just flipping the bras to kets using the CPT operator. So this is essentially a generalized version of that. This is essentially even when you're given any density matrix for some set of subregions, you can do the same purification, and that gives you some canonical purification. Now, the object that I'm going to talk about here is the reflected entropy, which is defined as follows. You compute this this canonical purification, square root rho AB, and then compute the entropy of the subregions A and A prime. So you started with AB, double it to AB, A prime, B prime, and then cut it across to get A and A prime. That defines some sort of entanglement measure. And this was defined in a paper last year by Datta and Faulkner. And just to give you some motivation for why we care about this quantity, firstly, it's a measure of bipartite correlation. For pure states, there's a canonical measure of bipartite correlation, which is just the entropy, the entanglement entropy. But in the case of mixed states, there's no canonical measure. We have many different measures which all quantify different aspects of correlation. So two familiar ones are just the entropy and the mutual information. And this is some other measure of bipartite correlation, which is nicely sandwiched between these two different quantities. Also, it captures both quantum and classical correlation. So different bipartite correlation measures have different weightings of how they weigh quantum correlations and classical correlations. This one captures both, although in some sense, it's like more sensitive to quantum correlations, which I'll try to argue later. But most of all, the reason that we care about this quantity is that it has a very simple holographic dual. This was proposed in the paper by Datta and Faulkner, where the dual is as follows. So suppose you have the picture here is, say, a time slice of ADS, and you have two regions, A and B. And the surface marked here is the Ryu-Takenagi surface, which is the minimal surface anchored to the endpoints of A and B, which I've called here gamma AB. This marks a region in the bulk, which is this blue shaded region, which is called the entanglement wedge. The entanglement wedge has been really useful over the last few years in understanding bulk reconstruction. And essentially what it means is that the density matrix on A and B essentially captures bulk information in this blue region. So very naturally, this blue region is associated to the regions AB. Now, given that, the reflected entropy was proposed to have the following dual. You compute the minimal cross section that divides the entanglement wedge, which is this blue region, into a region homologous to A and a region homologous to B. So this surface is here, the minimal surface that does so. And that's what I'm calling EW of AB, which is the minimal entanglement wedge cross section. Now, clearly this is, and when I say twice the entanglement wedge cross section here, we just mean the area of this entanglement wedge cross section in units of 4G Newton, as is familiar from other examples like the Ryu-Takenagi formula. Okay, so one thing to note is that this is an extremely sensitive measure of the connectivity of the entanglement wedge. So in this example, suppose you were to look at these regions instead, these C regions, then the entanglement wedge has two disconnected portions, which are these red regions. And there is, I mean, in this case, it's clear that you don't need an entanglement wedge cross section to divide the entanglement wedge. It's automatically divided into two parts. And so the entanglement wedge cross section is 0. So the reflected entropy turns out to be an extremely sensitive measure of how connected the entanglement wedge is. In the disconnected phase, it takes the value 0. And in the connected phase, it takes a value, which is a large value. It's a value of order 1/G Newton. Okay? So that's part of the motivation of why we care about this quantity. Note that there was also a separate proposal, which was the entanglement of purification, which was in these two papers by Umemoto and Takenagi, and also Brian and his collaborators. The EP, which is the entanglement of purification, requires an optimization over a lot of purifications, and it's in general much harder to compute. And this reflected entropy, as we'll see, is something that you can compute in models and get reasonable answers. So that's why we focus on this one. Okay. So the intuition behind such a proposal is essentially pretty simple. You want to find the geometry that's dual to the state square root rho AB. So square root rho AB was this thing where you had a doubled version of the state living on AB. And we already know from holography and work on bulk reconstruction and so on that the region in the bulk dual to rho AB is this blue region, the entanglement wedge. And so it's natural that the state corresponding to this canonical purification is simply a doubled copy of this entanglement wedge, which is now glued at the relevant surface, which is this Utakinagi or HRT surface in the time-dependent case. And so if you glue together two of those blue patches at this surface gamma AB, what you get is something like this cylinder. So I'm drawing here a spatial slice of the geometry dual to square root rho AB. And it essentially contains two copies of these entanglement wedge, which is glued here. And now the reason this really works is because you're allowed to do this. So naively, I mean, you could guess that you can double this geometry by just gluing them together, but you also have to make sure that Einstein's equations are satisfied. So the constraint equations need to be satisfied. And this actually turns out to be the case because of the fact that the HRT surface is an extremal surface. You're always allowed to glue together spatial slices at an extremal surface and get consistent initial data which solves the constraint equations. This was shown in a paper by Engelhardt and Wall. So once you have all of this, essentially you have a geometry dual to a state square root rho AB, which is holographic. And so you can just use the Ryutakinagi formula. So for the Ryutakinagi formula, if you want to compute the entropy of A and A prime, we need to compute the area of a surface that's homologous to A and A prime, and that's minimal. Naturally, the surface that shows up is this red surface here, which is essentially, if you trace back to the blue picture, this red region here is one copy of the entanglement wedge cross section, and the dotted line is another copy which came from the doubling. And so essentially the entropy of AA prime is given by twice the entanglement wedge cross section. So that's a simple way to see why this proposal should be true. Datta and Faulkner went through a lot of other arguments to actually emphasize that something like this should be true. There's a simple generalization to this, which is essentially that you can apply this to situations where there are these entanglement islands. The entanglement islands played a key role in understanding the page curve in holography last year. And you can generalize the story of the reflected entropy to this. This was something we did in a paper with Ven Chandrasekaran, Masamichi Miyagi, and myself. And so the familiar setup that people used in these calculations of the page curve was where you have, say, some region of gravity, which is this middle region. So let's say for a specific example, you can consider JT gravity. And the gravitational region was glued to a flat space region on either side, which then allowed the black hole to come to equilibrium with this flat space bath. And then there was a naive information paradox at late times, which could be resolved by the inclusion of this island. This was the story of the page curve for entanglement entropy. But you can also run into similar problems for the reflected entropy if you don't use a similar islands proposal. And the simple fix is motivated by the holographic dual, which is you simply take the island, and now again, you want to split it using a cross section, which is this red dot here, into two parts, one which is homologous to A, one which is homologous to B. And now the reflected entropy gets two contributions. There's the usual reflected entropy computed in the effective field theory, plus this cross-section contribution, which comes from this red dot here. So this is some simple generalization of the holographic story. Now, another toy model where we can think about this is tensor networks. So tensor networks have served as a great toy model for holography. They satisfy various things, various features that you see in holography, in particular, the Ryutakinagi formula, quantum error correction, other properties that you'd like to see. And there's a particular example that I'm interested in, which is the random stabilizer tensor networks, which were proposed in this paper by Hayden et al. And also in a paper by Nizami and Walter. The idea is simply that you take a spatial slice of ADS, discretize it using these tensors. So each of these tensors discretizes this geometry into some graph, and the edges sort of tell you about the geometry. And now once you have a graph, minimal cuts in the graph are well defined. And so you could think of those as like discrete versions of minimal surfaces. So the Ryutakinagi surfaces could be as follows. These surfaces represent some Ryutakinagi surfaces. And the pictures that we draw here are very familiar, very similar to what we saw in the case of the ADS picture. And so you could guess that, well, what I do is simply glue this tensor network together, and you have the same picture that we had with the cylinder. And then applying the Ryutakinagi formula again, you should get something like the cross section. However, this doesn't quite work. And the reason it doesn't quite work is basically when you take these two copies of the tensor network, you have tensors on both of these copies, which are actually correlated. And for the proof of the Ryutakinagi formula, it was important that these tensors be uncorrelated. In fact, in this paper by Nizami and Walter, what they showed was that if you consider random stabilizer tensor networks, note that stabilizers are a special class of these tensors, which have very good error correcting properties, which makes them amenable to calculations. What they showed was that the entanglement structure of these states is actually very simple. It's basically bipartite. So if you have regions A, B, and C, the entanglement structure is such that A is separately entangled with B and separately entangled with C, and B and C are also entangled with each other, but there's no non-trivial tripartite entanglement. This is what was called the mostly bipartite conjecture in a paper by Matt Hedrick and collaborators. So in this paper with Chris Akers, what we showed was that, well, if you just consider this mostly bipartite conjecture, that already implies that the reflected entropy equals the mutual information. This is something that's easy to calculate. However, in holography, there are situations where there's a large difference between the reflected entropy and the mutual information. These can be very different measures. And small non-perturbative corrections don't really change the story. And so there's a robust sense in which you really need tripartite entanglement to model good holographic states. And the random stabilizer tensor network is just not good enough. Very good. So
sorry, I'm a bit lost, Pratik.
Oh, I'm
can
so
I
sorry.
interrupt?
Yeah. Yes, please.
So I'm a bit lost in this slide. What exactly tripartite you mean? What are the three parts that you're talking about here?
Good. Sorry. So I should have said this. So what I mean is you have A, B, and C. These are some three regions on the boundary. The entanglement structure essentially is like this. There are bell pairs shared between each of these parties. I mean, there are some simple unitaries that you can apply on each of the individual parties to break the entanglement structure into this simple form. So not all entanglement can be put into this form. And so this is basically the structure that the mostly bipartite conjecture is basically proposes. It turns out that random stabilizers actually have this form, but what we wanted to argue was that holography is nothing like that. Does that clarify your question?
Well, I got that, but what is that? What does that had to do with these diagrams that you did, that you drew, this tensor network diagrams?
Yeah. Okay. Okay. So let me just say this in a different way. So the initial idea was that tensor networks have a very similar structure to holography. And we know that they satisfy things like the Ryutakinagi formula and so on. And so you could hope that they'll also satisfy something like the proposal for reflected entropy. And it also looks like that at the level of pictures, because you have these two copies which you can glue together and get something like this cylinder geometry. And what I wanted to emphasize was there's a simple reason why that doesn't work. The reason it doesn't work was because there were correlated tensors on both sides. And a way to see that is this is the fact that they actually have very simple entanglement structure, and you can actually independently compute that the reflected entropy is actually equal to the mutual information. So clearly it must be the case that this cylinder picture was actually misleading. Although we'll see that there's this, like you can improve this picture to actually make it correct.
I see. So you're going to talk about the tripartite. My question was, how does the tripartiteness enter into this construction? So that is something you're trying to propose something. You're going to talk about it probably.
Sorry. Yeah. I'll get to that. Yeah. Thanks for the question. Yeah. Also, please interrupt me. I mean, it's okay if I don't finish the talk, but it's better to have everyone on the same page. Yeah. Yeah, so this was, so what I wanted to emphasize here was that these were, for the random stabilizer tensor networks, they had this simple entanglement structure, which led to this contradiction with the holographic proposal. But, and so whatever models holography, I mean, whatever model you think of it, it has to have this feature that it has reasonable amount of tripartite entanglement in order to reproduce the holographic proposal for the reflected entropy. So this is some sort of more refined measure of entanglement. And so the lesson is going to be that tripartite entanglement is actually very important to model these holographic states. So can we come up with a model for such holographic states? Well, it actually turns out that we can actually do much better with random tensor networks. So note that these are not stabilizer tensor networks. Stabilizer tensor networks were where you pick each tensor to be from this stabilizer group. And in the lesson of this talk is going to be that those weren't random enough. On the other hand, you can just pick Haar random tensors. And in this paper by Hayden et al., they had showed that these also satisfy the Ryutakianagi formula. But all the calculations earlier were with regard to entropy and so on. But in this paper, what we'll show is that this model will actually have the correct tripartite entanglement structure in order to actually reproduce this holographic proposal. So hopefully that clarifies what the goal is here. So let me just overview what I'll be talking about here. So we'll start with introducing these random tensor networks. We'll talk about the replica trick calculation, which will give us all the answers that we need, and how it connects to holography via what I'll call fixed area states. In particular, there will be phase transitions in these quantities, and we can actually analyze all of these phase transitions. So that's the page curve part of it. To make you familiar with the ideas, I'll first talk about the entanglement entropy and then talk about the reflected entropy for different models. And then finally, I'll conclude with some outlook. So just to clarify, random tensor networks are defined as follows. You define some graph G, which is like some discretization of the geometry that you want, which has some vertices and edges. So a simple model here is where we have these two vertices, X and Y, and there's an edge connecting them. Now, what you can do is pick random tensors. So these Vx are some Haar random states that you pick at each of these vertices, and then glue them together using maximally entangled states. So you sort of project them onto the maximally entangled state. And what you're left with is a graph which has closed edges and some open ends. Now, the open ends will, so basically this graph, this tensor network will define some state which lives on these boundary ends and which has this geometry of the tensor network of the graph G. Okay. So there's a simple fact which will actually be the key player in this game, which is that when you take these random states and take n copies of them, and then you average over them. So this is the Haar average. You're integrating over the unitary group to get the average of this particular object. It has a very simple form. It just reduces to a sum over these elements, which are permutation group elements. So you can think about the permutation group on n objects, which basically permutes these objects in different ways. This forms this symmetric group sim n. And this average will end up being this sum over these different permutation group elements. So as an example, suppose you were to compute the Rainey entropy, what we usually compute is this trace rho to the n. Trace rho to the n will also have this form where it reduces to a sum over these permutation group elements. And it's like a partition function on a model where each of the elements at the vertices are some element of this permutation group. So the way you can think about this is that there's a replica trick on the boundary, and there's some way in which the replica trick sort of extends into the bulk. And so these permutation group elements essentially capture the way the bulk is glued together. Just for some intuition, that's the way to think about it. So once you've reduced this calculation to this Ising model-like action, Sorry. This partition function has an action which is given by something like this, where there's a weight associated to each edge, and there's some weight computed by this distance. So there's some distance measure on the set of permutations, which is called the Cayley distance, which is essentially how many flips it takes to go from one permutation to another. That's some measure of distance between these. And so it's like an Ising action where you measure the distance between these two. So if they're anti-aligned, there's some energy cost. And the cost is weighed by the size of the bond that's gluing them together. Okay, so that's the action in the bulk. But you also have boundary conditions because you're computing some quantity trace rho to the n. Trace rho to the n, it should be familiar. It has this form where you just glue the A bar copy to itself, but A has this twist operator acting on it, so it acts cyclically. And so the boundary conditions will essentially be that in the A region, you have some cyclic permutation that's acting, which is doing this trace rho to the n. And in the A bar region, it's just the identity. So it's a trivial thing. So now how does this relate to holography? Well, when you compute this partition function in the large D limit, essentially it's a saddle point approximation, and the minimal energy solution is as follows. So at A, you have a cyclic permutation acting. The cyclic permutation extends into a domain in the bulk, which is this blue region. The identity permutation acting on A bar extends into this red region. And there's some domain wall which separates them. The domain wall will essentially turn out, oh, sorry, yeah.
Pratik, we are not able to see the red, blue.
Oh, wait, why did that happen? Can you see it now?
Yes.
I'm so sorry, there was some glitch here, yeah. Okay, so just to repeat what I was saying, the region A has some cyclic permutation domain associated to it, and there's some identity domain attached to the A bar region, so that's this region. And there's a minimal surface domain wall that separates them. And this domain wall will essentially turn out to be the Ryutakianagi surface. So there's the only energy cost in this model will come from this domain wall. And in particular, using the fact that the distance between the cyclic and identity element is n-1, we'll end up with the Renyi entropy being given by this gamma log D, which should be interpreted as the Ryutakianagi formula. So the Ryutakianagi formula essentially comes from this picture where you're summing over domains of different permutations. That's a different way of deriving it. Now, this is actually extremely closely related to holography, and the reason that is so is because there are what are called fixed area states. This was something we defined in a paper with Chris Akers and also separately in a paper by Dong Harlow and Marolf, where instead of using states which are smooth in the bulk in general, what we can do is prepare states with the path integral where everything else is as usual, but instead you fix the area of the minimal surface on this slice. So this is something that's analogous to being in the microcanonical ensemble. So in the canonical ensemble, the area has large fluctuation. There's some distribution over areas. But what you could do is try to narrow that window into a small window peaked at some value of area. So you can fix this area, but then if you fix one object, then its canonically conjugate object has to have large fluctuations, and that results in this conical defect. So usually the way we solve, the way we prepare states using path integrals is having smoothness conditions in the bulks. There are no conical deficits. But now instead we choose the boundary condition where there's actually a conical deficit of arbitrary value at this point, such that it fixes the area of that surface. So using these states, it actually connects well to the random tensor network for the following reason. Suppose you were to compute trace rho A cubed, so trace rho to the n for the Renyi entropy calculation. What it'll essentially do is take 3 copies of this Pac-Man diagram, which is basically the 3 density matrices, and then glue them in a cyclic way. So you glue this copy here, and this copy here. Okay, so the way you can think about this is as a permutation. So you didn't have to resolve for the geometry at all. The advantage of using these fixed area states was that it's the same geometry, but all you had to fix was a gluing procedure. So the gluing procedure was 1 goes to 2, 2 goes to 3, and 3 goes back to 1. So you can represent the gluing by this permutation. And this is quite different from what you would do in the canonical ensemble. In the canonical ensemble, you would have to resolve for the geometry to ensure that there is smoothness. But here, all the boundary conditions are satisfied by having this fixed area and just gluing the surfaces together. So this simplifies a lot of things. And the structure of the calculation here is identical to what you see in the random tensor network. Using this, you can analyze phase transitions in the entanglement entropy. So suppose you have this 2 intervals case where there are these 2 possible surfaces, the connected one and the disconnected one. You have a similar picture where there's a cyclic domain and an identity domain, but there's this whole middle region. This middle region has some arbitrary permutation that you can apply, which is not a priori fixed. And it'll actually be non-trivial in the limit where you approach the phase transition. So you can draw similar pictures for the fixed area states where now you have these 2 surfaces, gamma 1 and gamma 2, which are fixed, and they have some conical deficit at them. And what will end up happening is that near the phase transition, you'll have sort of 2 domain walls. So there's a domain wall between this tau and cyclic, and there's a domain wall between tau and identity. Now, because of that, you get these 2 contributions. There's a contribution from the area of gamma 1 and the area of gamma 2. So there's contributions from the connected and disconnected surfaces. Near the phase transition, suppose you're like very close to both of these being equal, there are actually extra contributions that become important. So even in the large D limit, there are actually a class of new saddles which become important. And there's a very simple way to characterize what they mean in terms of the permutation group. In terms of the permutation group, they actually satisfy this equation, which is essentially the triangle inequality. They saturate the triangle inequality on this distance measure. And that just means that on this Cayley distance measure, if you look at the line between the identity element and the cyclic element, there are elements tau which lie on this line. So they're essentially the ones which lie on this geodesic. And that's a very nice way to classify what these saddles are. And there's a well-known classification of these, which are called the non-crossing permutations. These non-crossing permutations became extremely important in these calculations of the Stanford replica wormholes paper and also other papers which analyzed phase transitions in entanglement entropy. And what they look like essentially is you have some gluing pattern where it's not cyclic, but you're allowed to glue in this different way, as long as these don't cross. So each of these lines can be represented by a permutation of this form. So when you have 9 copies of the boundary, you can glue them in this way. And as long as these lines don't cross each other and they have the right orientation, that's what we'll call a non-crossing partition or a non-crossing permutation. And these class of saddles become extremely important at the phase transition. So you need to take into account the contribution of these. So if you were working in the saddle point approximation, you could work with either side of the phase, but near this phase, you need to add them all up. And so it's some combinatorial problem to resum the contributions from all of these saddles. Now, a way to do this is something that was introduced in the Stanford replica wormholes paper, which is the resolvent trick. The resolvent is something where you can think of the resolvent as a generating function of the different moments of trace rho A. So trace rho A to the n can be computed using this sum over saddles, where you include the non-crossing permutations. Once you compute this, it's some sum which you have to do. It's this combinatorial problem that's well known how to solve. You can then compute the density of states from the resolvent. And there's a well-known density of states, which is called the Marchenko-Pastur distribution. and you use that to compute the entropy. The entropy is the page curve. So this is something that should be very familiar. So instead of having this entire network, if you just had a random state, a state between two parties, there's an analog of the disconnected and connected surface. And as you cross the page curve, you essentially go from one to the other. So this is essentially, this is just a reproduction in a different way of the calculation page did. But this technique of using the resolvent will turn out to be useful for us. So the main lesson from this review is that replica partition functions computed in the random tensor network are in fact identical to those computed in holography, as long as you use these fixed area states. So there's a precise connection between these, and the sum over permutations in the case of the random tensor network is identical to the sum over these relevant topologies in the case of holography. And there's a precise match between these. So that is sort of the main lesson. This lesson is exactly what allows you to check that all the holographic proposals you could derive by the replica trick in holography will actually turn out to be true in the random tensor network, and hence the random tensor network can be seen to be a good model of holography. It'll have the right entanglement structure and all of that. So at this point, let me pause for questions if there are any. Okay. Okay. So this was for the entanglement. Oh yeah.
Sorry, I actually maybe have a short question. So in this random tensor network, what is the key point to be that is responsible for this feature of reproducing holography? Yeah, so is this the Cayley distance? Okay.
Thank you for that question. So the key point is this. So the key point is this fact. It's the fact that the average over these random tensors is a sum over permutations. The Cayley distance is just something that encodes the distance between these permutations and so on. So that naturally follows once you have this. And the way to think about it is like in holography, what you do really in the bulk is essentially figure out how the gluing on the boundary extends into the bulk. And so this sum over permutations is essentially a way to see that. It's just you prepare the same state and glue it in different ways. So the fact that the random tensors gives you a sum over permutations is the key thing that matches the fact that in holography, you'll sum over different saddles with different topologies. So that is the key point.
So it is kind of replicating this what is it called, the complete set of states that the fixed area states acting like a complete basis in at least in a
roughly. So in the fixed area case, we only fix the area of the HRT surface. The random tensor network actually does more. It actually fixes the areas. It effectively fixes the areas of all surfaces, which is not really what holography does. So as long as the only relevant surfaces in your computation are space-like separated from each other. So if they're space-like separated, then you can fix the areas simultaneously. They commute with each other. And as long as you can do that, then the only relevant saddles will really come from those surfaces, and then these calculations are identical. There's a sense in which the random tensor network does more than what holography wants it to do. And so then when you start probing things like, for example, the entropies of crossing regions, you can't fix the area simultaneously, and then it won't match with holography. But as long as you're restricted to surfaces that are space-like separated, so for example, the disconnected and connected surfaces were space-like separated, and so it's fine to do that. And in those cases, the random tensor network calculation will be identical to the holography calculation.
Thank you.
Thank you so much for that question. Okay, very good. So now we can move on to the reflected entropy, which is sort of very analogous to what we did, but slightly more complicated. You still need some replica trick to compute this quantity. And the replica trick was discussed in the paper by Datta and Faulkner. So what you do is there's the familiar replica index n, which is just computing the Rayleigh entropy. But on the other hand, you also need to compute it for the state square root rho AB. And the way to do that is introduce another replica index. So there's another replica index M, which is used to prepare the state rho AB to the M over 2. And so this 2-parameter replica trick then gives you some quantity which can be analytically continued. When you analytically continued this to M equals 1 to get a square root here, and N equals 1, that gives you the reflected entropy. So what you want to do is perform this replica trick and do this analytic continuation and get the answer. Now, this is some slightly more complicated replica trick. And the way to think about it is essentially you have N times M copies of the system with some particular boundary conditions, which is the way in which it's glued together. So if you want to prepare the state rho AB to the M over 2, you can take M over 2 copies of the state and then glue them together. Similarly, you can take, to prepare the ket, you have another M over 2 copies and you glue them together. And now once you've prepared this density matrix for A, AB, AB, A prime, B prime, then what you want to do is compute the entropy for the region A, A prime. So you'll again now apply a twist operator. So the way to think about this is in the B region, now you want to glue them trivially. And so that'll just take the ket region, which is below, and the bra region, which is above, and glue them together. So this is what the permutation applied to B looks like. It's some complicated way in which it's glued, but it's essentially what follows from this replica trick. And similarly for A, what you'll do is now take the upper half, which was the bra, and the bottom half, which is the ket, and perform this twist operator. So there's a twist operator which will cyclically permute the bottom halves. And once you permute those bottom halves, then now you can glue them together and it gives you the familiar Renyi entropy of AA prime. So this is what the calculation looks like. And let me describe it in a particular example. So consider a single tensor which has 3 parties. So it's a single tensor of this form where it has 3 bond dimensions, dA, dB, and dC. This is sort of a toy model for a sort of 3-boundary wormhole where the bond dimensions can be thought of as these blue surfaces, the areas of the mouths of the different wormholes. So once you have this, and also you'll want to fix the areas of these surfaces, which you can because they're space-like separated. Once you have this, the calculation in the random tensor network should be identical to the calculation in this 3-boundary wormhole. Now the holographic gives you some curve like this. This is what we call the page curve. And the way to understand it is pretty simple. For small values of bond dimensions of A and B, the solution tends to be in the disconnected phase. So these 2 surfaces A and B are small, and so you want them to be the minimal surface. Whereas when these are large, then you want this surface C to be the minimal surface. So there's a transition from the connected to the disconnected phase. And as we saw earlier, in the disconnected phase, you expect that the answer is 0. So the reflected entropy, which is this blue curve, is 0 in the disconnected phase. But as soon as you go to the connected phase, it jumps, and it jumps to a finite value. So an interesting part of this page curve is this discontinuous transition. This is unlike the page curve for the entanglement entropy, which is continuous, but it has a kink. This one is in fact discontinuous. And so what we want to understand is first how to reproduce this calculation and how to resolve this, this page curve. Okay. So the basic thing you can try to do, which is the first thing we tried in the entanglement entropy case, is the saddle point approximation. So first you want to figure out what far from phase transitions, what are the relevant saddles that show up. And a useful way to think about it is with the Cayley distance. So the Cayley distance induces a graph on these different permutations. And the relevant permutations that we have are these identity, the permutation acting on A and the permutation acting on B. And they have some sort of complicated structure, which takes this form where as you want to go from identity to GB, there's sort of this fork. In going from identity to this point X, you're actually on the geodesic for both. So it's a common geodesic between identity and GA and identity and GB. And then at some point you have to make a choice, and there's a geodesic to GA and GB. And separately, there's some other geodesic between GA to GB. So this is some toy version of what the Cayley graph looks like. Most interestingly, there's this piece which is a common on the geodesic. Okay, so using that, what you can do is figure out what the phase diagram looks like. So if you're in different regimes of dA, dB, and in units of DC, suppose you're at large dA, then what you want to do is make the permutation of the tensor identical to A, because A is the strongest domain wall in some sense. It has the largest energy cost. Similarly, when you're at large dB, you want to make it the same as GB. And when you're at small dA and dB, you want to make it the same as the identity. So essentially what the tensor in the middle is doing is it's trying to match whichever gives it the least energy cost. Now, there's also an interesting region in the middle, which is actually a replica symmetry breaking phase, which actually does dominate. This is quite unusual in the case of the entanglement entropy, but there's a large region where this replica symmetry breaking phase dominates. However, what we wanted to do to compute the reflected entropy per se was to analytically continue n and m to 1. And that will actually turn out to simplify things. Firstly, we work with m greater than 2, because when you go to m less than 2, you find negative tension branes and things get messy. So we stay within m greater than 2. And then you can compute what the Rayleigh entropy is within whatever point you're at. So suppose you were at this point, then GA dictates what the answer for the Rayleigh entropy would be. And then you can analytically continue this. Now, this replica symmetry breaking phase is kind of complicated, but it simplifies in the limit when n goes to 1. So in the limit n goes to 1, it's actually not important because this point goes all the way down. And all you're left with is the three domains, identity, GA, and GB. Okay. So using that, what you end up with is in the identity phase, you have 0 reflected entropy. And in the other phases, you basically get what you would expect from holography, which is twice the cross section. So this is something that is very general. It wasn't particular to this example. In general, you'll find phases of this form. There'll be phases which are analogous to the disconnected phase, and there'll be phases which are analogous to the connected phase. This X region shows up, but again, it vanishes when you take n goes to 1. So in the end, you end up with the holographic answer. And this sort of clarifies the replica trick calculation that was done in Datta and Faulkner in a much more precise way. However, this is not sufficient to understand the page curve per se. The page curve will come from resolving this phase transition, which can't come from the saddle point approximation. And so we have to do something analogous to what we did in the entanglement entropy. So you want to compute the resolvent, which will now be the generating function for the moments of trace rho AA prime to the n. And so the question just becomes which topologies to include. This is a more complicated question than what we had in the entanglement entropy. In the entanglement entropy, it's well known that the non-crossing permutations are the thing that you should include. In this case, it's a little hard to prove which ones to include, but you want something that will include everything on the relevant geodesic. So you want something that interpolates between identity, GA, and GB simultaneously. And the simple guess that we made, which is a conjecture that we're reasonably confident of, is it's analogous to the entanglement entropy where you use these non-crossing permutations. So it's something that interpolates between the identity and the cyclic element within each of these cycles. But also you want to interpolate between the A and B elements, which have this twist operator. So you need to apply more permutations outside, which are also fixed by these non-crossing permutations. So this is it's something very analogous to the non-crossing permutations. It's just some choice of the set of saddles that you'll choose to include, which dominate. And this is sufficient to compute what the entanglement spectrum is. So there's a very nice picture. So if you want to remember something, maybe this is the key point here. There are two kinds of saddles. There are what we call the disconnected saddles and the connected saddles. The disconnected saddles are essentially the ones which are disconnected across this middle region that we cut open. So it essentially says that the bra and ket were not glued together. They were glued in some other cyclic sort of pattern. Whereas there are the connected type, where the permutation crosses this. And so these two families actually give you separate contributions. And it turns out to be very nice. So the disconnected type gives you a contribution, which is a single pole. So this is exactly what you expect from the disconnected phase in holography. In the disconnected phase, the answer for the reflected entropy is 0. And since it's 0, all that means is that the spectrum should just be a pole which has weight 1. On the other hand, the connected phase transition has an answer which is twice the entanglement wedge cross section. And so it should have the corresponding number of eigenvalues. And so the connected type, in fact, does give a similar distribution with the correct number of eigenvalues and the correct weight. The interesting thing that comes out of this is that there's a weight associated to each of these types, these two different types of topologies, which actually smooths out the transition. So you get a simple spectrum structure where this is from the connected part and this is from the disconnected part. And there's a trade-off between their weights. So if you're far in the connected phase, then this dominates. And if you're far in the disconnected phase, then this dominates. But they nicely, smoothly interpolate between those two cases. And you can think of this as coming from two super selection sectors. There's a super selection sector where the entanglement wedge is connected, and there's one where it's disconnected. So this weight is something that's computable, and this is sort of the key point of the talk, which is you can compute this exact transition where the weight goes from 1 at the end of the disconnected phase to 0 at the end of the connected phase. And this is some definitive thing. You can check it with numerics. It works very nicely. And so that's why we guess that the conjecture is actually pretty accurate. So this finally gives you the holographic answer with a smoothing out of the transition. So this is something which we also expect to be true in arbitrary random tensor networks. This was just in the single tensor example, but something similar also happens in an arbitrary tensor network. You basically have some probability of being in the connected phase and some probability of being in the disconnected phase. And there's an interpolation between those. Okay, so with that, let me summarize. The key point of this talk was to emphasize that random tensor networks are actually great toy models for the replica trick in fixed area states in ADS-CFT, and the math is pretty identical. And a particular example of that was when we computed the reflected entropy and showed that the holographic answer, which is 2EW, works out fine. And in fact, we went further to actually resolve this page curve of the reflected entropy. And as outlook, I'd like to emphasize that this resolvent trick was a useful technique which fixes issues with the naive saddle point approximation. This was also noticed in a paper recently by Chris Akers and Jeff Pennington, where they pointed out that the quantum extremal surface formula gets large corrections because of important things that come from this resolvent trick. So in general, this seems like a useful technique to understand better. The random tensor network tells you what kind of topologies should be important in ADS-CFT when you're doing this replica trick. Although without fixed area states, finding the solutions are much harder. I mean, it's similar to computing the Rayleigh entropy. In the Rayleigh entropy, you have to actually solve for this new saddle, and it has no simple description in terms of the original saddle. So I expect something similar to hold for the reflected entropy. Further, we also emphasize that this simple bipartite entanglement structure is not very accurate of holography, and you need multipartite entanglement. And just from the fact that the random tensor networks have an identical replica trick, whatever you will compute, whatever multipartite entanglement quantity you will compute using this is going to reproduce what you get in holography. So it's a good model for the kind of multipartite entanglement structure you get in holography. And finally, the canonical purification had this nice picture where it led to these two non-trivial sectors. There was a sector where you had a connected phase and a sector where you had a disconnected phase with some different weights. And so this is in sort of the spirit of thinking of geometry as coming from entanglement. You just have two random states, you put them together by this canonical purification, and you get some non-trivial geometry where there's some weight associated to a connected geometry and a weight associated to a disconnected geometry. And so one would hope that you can push this further by using random states. Maybe you can build up geometries in some sensible way. And so all of this is work for the future. So with that, I'd like to thank you.
Thanks, Pratik, for a very interesting talk.
Thank you.
We have time for a few questions.
Let me just put up the summary again.
Okay, so maybe let me ask a question first. I come from a sort of quantum information theory background. So I had a very basic question about this reflected entropy quantity itself. It's very interesting thing to look at. So you had taken this two copies of row AB essentially. So you made it A prime, B prime, and then you looked at the bipartite cut A prime, B, B prime, right? And that gives you an entropy to look at. What about the cross cut, the A prime B and the AB prime? Have you looked at that?
Yeah, the A prime B cut, I think you can actually show that it's, at least in holography, it's kind of trivial. It doesn't give you any interesting like connected feature. It's actually possible to compute it. This was probably already done in the Datta Faulkner paper.
I see.
But maybe it's an interesting question in quantum information more generally, what that does. I think that's not well understood.
Yeah, because in the quantum information context, this thing is actually related to something called the operator entanglement, the second order Renyi entropy. Not so you look at the von Neumann entropy, but the second order Renyi entropy is actually related to something called the operator entanglement. And studying the cross entropy leads to a complementary quantity to the operator entanglement. So anyway, that's why I was curious whether in holography it leads to anything interesting as well.
I see. Okay, that's an interesting point. Thanks.
Prabha, I have a very short question, I think.
Sure, please go ahead.
So just one thing was that you're claiming that in this random tensor network and via your conjecture of understanding, I mean, your conjecture is about which saddles are dominant. And and then if you accept that conjecture, you find that the transition is not first order, but somewhat smoother. But that doesn't really reproduce holography, right? At least in the large and...
So so it depends on which example we're talking about. So let me just go back to the example we discussed. So for example, in this 3-boundary wormhole situation, as long as, okay, so there's a few caveats here. I'm assuming, and I think this is true, that there's a unique minimal surface, which is this mouth of the wormhole. And there's another caveat, which is that there's another possible entanglement wedge cross section in this situation, which comes from a surface somewhat like that. And there's no analog of this in the random tensor network. But you can actually tune the moduli of this wormhole such that that surface is not relevant. If that's true, then up to non-perturbative corrections, this will actually have the exact same, or as long as you're in fixed area states, it'll have the exact same calculation as what we did in the random tensor network. So it'll be the same interpolation. Now you could go ahead and ask, well, what happens in non-fixed area states, which is what we usually think about. And that's true, that's much more complicated. It won't necessarily reproduce exactly what you get in holography. But on the other hand, there have been recent calculations in the entropy where using the answer you get in fixed area states, you can actually approximate the answer in non-fixed area states pretty well. This might be a bit more complicated for the reflected entropy, but it's plausible that using the fixed area states, you can get some approximation for the answer. And once you have that, then you would have the exact form of this smoothing. This is actually something that does happen in the case of the entanglement entropy in the replica wormholes paper. In the replica wormholes paper, they have a calculation in the microcanonical ensemble, which is precisely the page curve we calculated here. And there's another calculation they do in the canonical ensemble. In the canonical ensemble, you can actually approximate the answer very well by some sort of integral transform of the fixed area answer, or the microcanonical answer. And so hopefully something like that will work out here as well. So it will be the same as holography as long as you tweak the parameters correctly. Does that answer your question?
Yeah. I actually lost you because of my connection issue, but I think I got it. Thank you.
Thanks.
Okay. Any further questions? Okay, if there are no further questions, let's thank Pratik again for a wonderful talk. And I think that draws the session to a close. Hope to see everyone tomorrow morning for the panel discussion.
No.
Huh?
Oh, for the panel discussion, yeah.
Yeah.
Okay, so okay, I have to give a little bit of ritual left to give this vote of thanks. So let me do that. So firstly, thanks to all the speakers. I mean, we are really humbled that you have shown so much enthusiasm and immediately agreed. And it is because of you, we have been able to give a fitting honor to David Gross. And it has been really a wonderful workshop. And also you have given us a very good lesson in our stretching our attention span. I mean, 9 into 5, 45 hours over the period of 5 days was really quite good. And I wanted to make sure that I could really focus on each talk. I don't know to what extent it has been successful, but it has been a great lesson and great exercise in attention span. And especially thanks to all the participants, because it's certainly not easy to just stare at your laptop for such long time and then virtually engage with so many people at the same time. But I think it has been very enthusiastic. All our sessions have been quite successful. So we thank all the participants too, and certainly thanks to all the chairs who have conducted all these sessions, because without them, it would have been impossible for us. And they have all done a great job in steering this conference. And then, of course, thanks to IIT Madras and the Department of Physics for giving us this opportunity to host this. And of course, and what else? And well, probably have nothing else to say, because maybe okay, forgive me if I'm missing anybody because I'm a bit sleepy. But I, in the beginning, already thanked the IT team for helping us design this website. And hopefully you liked our program, you enjoyed all the talks, and it was a good program. But tomorrow we should all join for this special panel discussion, if possible. If you can wake up.
Hello.
Yeah, he seems to be frozen.
So Ian has lost his connection, I guess. Give him a couple of minutes
Yeah.
to rejoin. So the panel discussion starts at 9:30 a.m. India time, I think.
Yes, it starts at 9:30. Oh, he disconnected.
Okay, he's back.
My internet connection. I think has spoken enough. So have a good time rest. Maybe we have to sleep, and you also take some good rest, and see you back. So goodbye to all, and see you back.
Thanks, Ian. See you all. Goodbye.